Okay, my name is Ghassan Regeb. Here we go. From Georgia Tech, and my co-presenter is Mohit Prabhashankar from Georgia Tech as well. So we'll talk today about our work in information machine learning. So before we start, if you can scan this QR code, you'll be able to download the material and access the material. So I'll give you a minute to scan. Just for logistical purposes, so the break is at 9:30, the coffee break. So maybe we'll take a few more minutes from the coffee break, but we'll try to stop at 9:30, 35, and so on. Okay. Okay. So all of us, we have experienced basically the difference between, what really foundational models are really promising us and the reality, right? And that has been the case for almost all deep networks. You design them in testing, they're really amazing. However, in deployment, there is always some issues. And in foundational models, it's becoming a problem because the public, basically, what they expect from the foundation model, but the expectation the AI model is really doing, the foundation model is doing everything, right? But in reality, it still has limitations. So an example, as most of you, if not all of you, are aware, basically SAM, the segmentation model, basically was released almost a couple of years ago. And it was trained on a huge amount of data. And besides its really powerful segmentation utility, but also it allows the human to interact with it. So the human can really prompt and interact with the model. That's another element where the human can interact. For example, if you look at the cityscape for autonomous vehicles, that the old annotation or the annotation with it took around 90 minutes per slide or per image. So now you can imagine we can even use SAM to kind of give you the annotations for cityscape is a fraction of the time. So back to what I mentioned about the SAM and have this kind of interactivity with the human. Let's look at this image in here. This image is really coming from a new data set. The new data set is called point prompt. This is basically what we did. We have 15 or more, 17, I think, 15, 16. So we have 16 data sets. They range from natural images all the way to medical images and seismic and so on, where and deep water, underwater data, where basically we allow the users to really interact with the SAM on the data sets. So we have collected 200,000 prompts on 6,000 images, and this is one of them. And there are a lot of findings in the paper and the data set, but I just want to pinpoint one of them. So for example, in here, this is a baseball player, and what you are trying to do is really kind of to segment the bat, right? And now the user, basically, you give them they have this capability to add inclusion points in the green and or exclusion point in the red. What I want to look at, I'll show you a zoom in version right now. But on the right hand side, you can look at the black curve. Basically, this is the different performance for the intersection over union between basically the segmented bat and the ground truth segmentation of the bat. Right? And I just want to keep in mind, basically going from left to the right. So basically, this is the user going from left to right. So the user is really kind of prompting and say, okay, they prompted for part B, and it's okay, I can do a better job. So let me really do a better job and see what happens. What we observe, this is across the 600 images, across the 200,000 prompts. The user, when they over prompt, the performance actually drops. And here's an example of what's happening. So this is the B one. You can see there are two green points. These are the inclusion points, and there's an exclusion point here, right? So this you get this segmentation, right? And then the user say, okay, I can really do a better job. Let me really kind of try to. Maybe the user say, oh, maybe there is confusion between the bat, the color is white, and the pants, the color white. So the user, what they did, and this is a real user, like not like somebody we are making up. So it's one of the people who really did the prompting from the public. What they did basically, they included the two inclusion points, the green, and then the exclusion point is on the pan, right? Because the same color, right? actually, if you look at the segmentation here, actually it's worse than the one before, right? So it's when they are over prompting, things become even worse. And the same thing in here. The user said, okay, now let me include the 2 inclusion points on the bat, 1 exclusion point on the pants, and then 1 exclusion point on the grass, right? So all the way to the right, right? So it is really kind of, I want to make sure everything surrounding the bat is an exclusion and the 2 inclusion points on the, and you can see basically if you look at, compare the segmentation here compared to the first one is much worse, right? It's worse. And that actually is shown in the intersection over union in the graph on the right-hand side. Although the model is thinking is doing a better job, but in reality, actually, the performance is worse. And that has been kind of, this conclusion has been across the board among 200,000 prompts. The user, they get a little bit more confidence, the over prompt, as the over promptings become worse. So there's another example. This is another data set. And again, whatever we are showing, you can find the QR code in the top and a citation at the bottom of the slide if you are interested in looking at this in more detail. So this is a new data set called DAR-AI, or Daily Activity Recognition AI. And this idea, basically, you have 20 plus sensors on the body and the environment, LiDAR, radar, and so on, and body sensors and environmental sensors on the human in the living room and the kitchen. Right? And they're doing many different tasks like cooking and eating and studying and emailing and doing Zoom meeting and so on. And basically, you can really feed this into like in this case, it's the lava that is there, and then you ask the questions, right? And there are questions in here. What is basically where is the jar, and then what's he doing, and so on. You can see basically the answers are really color coded. So the green means it's really correct. The red means it's not correct in this case. And you can see there is quite a bit of mistakes in here. If you notice, the mistakes are really coming from the system is really, the model understands very well the environment, right? But it doesn't understand the interaction, the activity, what's happening. The interaction between the human and the objects, the interaction between, and we have some other videos where between different humans. So this kind of fine-grained, based kind of, environment interactions is completely missed. And then here, basically, the model is we can say, like, it's doomed to choose, right? It has to make a decision. It has to tell you something. It could have just said, I don't have enough information, or I need more information. Maybe move the camera to the right, or zoom out, or I want to have another, because we have 20 different modalities in this data set. So the whole idea in here is that the model basically in this case doesn't have enough information, but at the same time it doesn't really admit it doesn't have enough information to answer some of the questions in this case. Again, in the same data set, in this case, I was talking about, kind of we have the activity, but actually we have kind of hierarchy there. So we have the activity, we have actions, we have procedures. So you can think of them as a pyramid. So at the very high level, you have the activities, and then we can split these into an alphabet of actions. And then each of these actions is split into even more finer grain into procedures. And this is all in the data set in this case here. And we can just look at the performance on the curve on the right-hand side. And in this case, basically, we look at the 3 different, like, how are we doing in recognizing activities? How are we doing recognizing actions? And how are we doing recognizing procedures? And you can see, basically, we're doing very good job at the activity level, but once we go to the fine grain, the performance really drops. It drops in this case on the green one in here. So in the fine grain, basically, we have an issue there to do a good job as we do in the activity, which is not really surprising. But also in here, the same data set, because we have multiple cameras and we have multiple LiDAR. So there is quite a bit of a domain shift issue, right? So the model cannot really adapt to a change in the viewpoint. So the 2 curves in the green and the blue on the right-hand side, these are coming from 2 different cameras. So at the activity level, both of them at both point of view, I mean, the performance is relatively comparable. As we go to the finer grain, which is the actions, actually you say there is a big gap. And as we go to the next hierarchy level of the procedure, you can think of them as kind of alphabets at a very short period of time. Like say, I'm cooking, that's my activity, right? Or I'm making salad, right? And then the actions, I'm getting veggie from the refrigerator, right? And then the procedures, basically, I'm holding this kind of the veggie. I'm holding a knife. So these are the procedures. Very, very short period. And we are doing it especially, it depends on the viewpoint. There's a huge gap in the performance between the two different viewpoints. So there's a domain shift issue that's really happening in this case. And again, there is also a bias that basically if you don't really create your data very well from in the training, then all what we have in the society as bias in our society, actually it will transfer itself into the model, right? So in this case, it's very showing in here. We have an image of a man basically kind of surfing on the wave, and then you ask the model what's happening, and they say it's a woman, right? And vice versa, like on the skiing on the snow, it says basically is a lady basically skiing, and then it says okay, is a man, right? So there are these kind of biases that they transfer themselves into this. So all of this talk about when you are really training on some data, right? We always try kind of to add as much scenarios in our training data as possible, right? So this is from the Belgium data set. What we did many years ago is to add 17 different distortions. You can think of them as compression, Gaussian, dirty lens, like sun's glare, environmental, as well as sensor, as well as processing distortions. And each one of them, we have 5 different levels of, like snow, for example, and rain as well is there. And also we try to really put as much of the possible scenarios in the data set as there, right? But all of these are really kind of, all of them are really, you can do your best at the training. But at the end of the day, when you really deploy this or in testing or deployment, especially that we talk about later on, then you will have this issues of novel data, right? You will always have this, right? Either it's auto distribution, there is some noise that you have it accounted for. There is somebody who really trying to do a adversarial attack on the model itself, for example. So we have the list of novel data is comprehensive, and the idea is basically how can you account for this novel data issues, right? So the first thing, okay, maybe we can do that at training, right? So this is this illustration really coming from autonomous vehicle work that we have done a few years back. So this is the real kind of performance illustrations from real data. So what we have in here for illustration purpose, we have 2 classes. So class 1 is in gray and class 2 in the blue. And then we start to play, and it's very clear basically where the boundary for us, right, between the 2 classes, right? But the question is, do I start with simple data where the information basically is low, or the tough data, right? The tough data meaning what? They are very close to the decision boundary, or they are really out of distribution, right? So if you look at the first case within the red box, right? So okay, let me start basically with these 4 samples, 2 from each class, and they're very far from bounding box. They are very clear basically what the distinction between them. These are the easy basically the ones, like the low information. So yeah, the performance will be very good at the very beginning, right? You can see that from here. Basically, it's this is the curve basically, and we get all the samples, and we're doing a decent job that way. But what if I count for somebody come and say, okay, let me account for the tough data samples early on, right? Very, very early on. So these are 2 are in the close to the decision boundary. These are ones seems to be out of distribution, or there's some distortion or some noise added to them. So we can start with these ones in here. And then basically when you start with this, we'll call it high information because these are tough samples. Decision boundaries seem to be like this. So you start with a very, very low performance, and then with more samples you start to compare there. But the conclusion in this case from that project that we had a few years back is that what we have it in here, you should not really start with this tough data, right, early on in your training, right? So it's very tough to account for this tough data early on. So the question is, okay, now, what if I, wait for it and include them in the training later on in the training, like a later stage in the training, right? So what if I do that? Then basically what we will do is a very well-known phenomenon, catastrophic forgetting, right? Because you start kind of, as you include this tough data late in the training, then basically you will forget about what you learned earlier on. There are many, many algorithms to account for this, to solve this problem in the training. However, overall, they really kind of degrade the performance to some degree, right? So now this idea of counting or accounting for the novel data in training is really tough. To make a decision about, like, do I include them early on the training or later on the training? right? So that's the big question mark, and there are some issues with what decision. This is with the assumption that you can have access to the novel data to start with, right? And in many cases, we don't really have access to novel data or all novel data that we can think of during the training. So what we are hypothesizing for the last few years is that the best way to really handle novel data is at the inference. So do a good job in the training, create a very well-trained model, but really account for the novel data at the inference. And the novel data basically is a long list of this. And I'm hoping that by noon today, basically, we'll be able to convince you that there is a merit behind basically this kind of hypothesis that we have been working on for quite a while. Okay, so with that introduction, we are splitting our tutorial into these sections. So I'll talk very quickly about inference neural networks. And I think for this audience, we'll go very quickly in that. And then we'll talk about explainability. And then Mohit will take over and talk about uncertainty and intervention before we conclude at the end. Okay, so let's get started with the inference neural network. And we'll talk about the basics, and then we'll move that to later on. So, I mean, as you already know, basically we have just very quickly some background in here. We have low level, we have medium level, we have high level features. That's what our deep network. The element is the neurons. In this case, we have a linear combination of the input. We have an activation function, the output. We put them all together basically into different layers. We have hidden layer, we have input layer, we have the last layer. Then you have your deep network in this case. And then because of the stationary property on images, then we can really start to look at the convolutional kernels, and that's what we have seen. Okay, so all of this is something as common knowledge by now. And then what happened basically in recent years, we start to have really huge amount of data. We have truly big data available to us to really kind of come up with these foundational models. And when you look at foundational models, it's really they're nothing but really transfer learning at scale. Really, I mean, really kind of you talk about billions of data, right? So until like 2019, mainly we rely on Resonate and so on. But since then, we are really relying on these foundational models, DALI, BERT, and Fleming, and so on. And basically, it's really transformer architecture, right? And then we always like to kind of share this definition of foundational model from this paper down there in the footnote about what is really a foundational model. How do you define where the name coming from? But the idea in here basically you have really kind of you have transfer learning at 3D scale, and then you have different kind of modalities, and you really ground them into the vision part. So all of this is kind of just kind of put us on the same page about where we are coming from. Okay, so now you train a model, right? And now back to what I was talking about early on. You have a trained model. You trained very well. It's a very trained model. And then at the inference, you input some data, right? So imagine the model was trained on all different aspects of a cat, right? And in this case, basically, this is the novel cat image because half of the but then his name is Milano, by the way, this cat. Half of there's half of the face not there. It's almost on the side, flipped upside. So it's kind of a novel data compared to what the model was trained on in this case. What we are hoping for, what aiming for, is that the data basically will be trained. The model will classify this as a cat correctly, and that's where robustness is. So as we mentioned, basically the way we are really training everything, and we are doing this inference deployment. Everything basically will be, we'll have the logic at the end of the network, and then basically a combination, and you can have a cat in this case. So now, when you have the training was done basically just have a combination of different features on the cat images, right? This different combinations of these features will give you a cat, right? So now when you input basically kind of a novel data of the cat, basically you're really trying to kind of you're biased, right? I mean you have this kind of a inductive bias toward those features, and basically trying to say, okay, I'm looking at those features and try to put them all together to kind of arrive at a cat or not. And sometimes you can, sometimes you can't. Right? I mean, you get the mistake in that sense. So that's where the inductive bias coming into the picture. Right? We would like to differentiate between two things. One is testing, and one is really deployment in the real world. Right? So in testing, what most of us do is really kind of an expert in the field, and we are really trying to do testing on many different images. We have access to a lot of data points. We do our testing. We do different analysis, but in deployment, we don't really have that luxury. But in deployment, but we have a model, we have a single sample, like you can take autonomous vehicle, medical imaging, and so on, and then you have to make a decision, right? It's that as simple as that. You don't have access to data, you don't have access to analysis tools, like that. So it's very constrained setting, what we are really focusing on in the next couple of hours. Okay. So let's look at these scenarios in the deployment case. So you have a trained model, if data there, this is already trained. You have an input image of a cat. It's an X in this case. The X really belongs to the shy base, which is the data that's really is not novel. And the model, as expected, will do a very good job basically saying this is a cat with an 89% probability. Right? Now, if you bring a different type of an image that hasn't been seen by the setup, because they have the face upside down, then this is the novel data, right? And in this case, I did still reasonable. It's cat 53%, the dog is 59%. However, it's the chances that this will make an error classification is really very, very high in this case, right? So now, in this case, how can we really handle the situation, right? So what we are hypothesizing is that you can really take care of these scenarios and add robustness to your decision at the deployment if you have really information provided by the novel data as a functional training distribution. Right? So basically, what you have a model is really describing a manifold, and now all what you have a single sample coming in, and then you would like to have information about how the novel data basically is a function of what you have in the underlying distribution, which is really kind of come from the training data in this case. So once you have that kind of hypothesis, then the question is, how can you really kind of extract this information, and then what kind of the way you can utilize this information to add robustness, and that's basically what we will show you. We'll show you how we can do this using something we call gradient at the inference, and we'll talk about that in much more detail in the next hour or so. Before we talk about that, let's look at the manifold, right? A manifold, basically by definition, what we will be showing you in the next few slides, the one on the left-hand side, just for illustration purposes. This is not really a realistic manifold. This is a very smooth, made-up, manifold. You cannot get a manifold that's beautiful. Usually, what we have on the one on the right-hand side, where we do a low-dimensional, processing on it, so just put it in a 3D or a 2D, so we can really visualize it and have it. But in any case, what we have in this case is you have trained model, you have this kind of manifold describing the underlying distribution. So let's look at the case. The case is what do we do, for example, in manipulating the manifold if I have access to a lot of data? So we can really look at two cases before I talk about what we do in the gradient and the inference. The first one is in self-supervised. Like in self-supervised cases, what you have basically you don't really have a ground truth, and you're trying to come up with a way. If you have the ground truth, then you can really kind of use that to say how good am I doing, right? But if you don't have that, then one of the methods is that you can just look at the SVD, just construct a covariance matrix, rank the SVD coefficients into this descending order, and then just look at how the performance. And this the first few in here is cipher 10, cipher 100, and ImageNet, and you can see basically this is the singular value rank, and then we have basically in here is the value. And you can see basically you have this kind of smooth in here. Now, if you look more carefully at the other ones in here, you have this kind of what we refer to as collapse. This is the dimensional collapse. And these are medical data like the breast, dermatology, OCT from the eye, OCT scans. You can see all of them, they are really experiencing this collapse. So this is a way to kind of describe or have a metric about the quality of the manifold that you are really creating, the representation space that you are creating. So the conclusion from this, and there is more on this in this paper down here, but a very quick conclusion that we can share in here: the natural image trained self-supervised training model is ill-suited to be utilized to like OCT, breast, and derma datasets, for example. Similarly, using the same setup in SSL, what we looked at is really just look at this idea of similarity of concepts, right? So imagine you have the classification of these birds. You have the first column is basically you have the ground truth, and you have basically now kind of explainability. And we'll talk about how we can obtain these heat maps later on in the tutorial. And then this one is for, the everything together. And here you have different components, color, shape, and so on, and structure. And then here we have three different self-supervised methods. You do the same thing. You create this heat map of concepts, again, for overall, for color, for shape, and so on. And then you start to compare. You can have the correlation between these, right? But in any case, in this case, we have the ground truth, right? So these cases in here, again, for the testing versus deployment, even if you just try to have a characterization of the manifold, these two methods, you still need access to either the ground truth or access to a huge amount of data to do these comparisons in this case. This is not the case we are talking about in here. We are talking about all what you have is just a sample at the deployment, and then you don't really have all that knowledge about the manifold as you have it in the training, right? And you don't have access to other samples, right? So what are your options in this case in here? So with this kind of very constrained situation. So before we do that, we look at basically this manifold. For example, if you look at traditional Shannon theory, we have you can really train event based on the combination of all the different events. In this case, in here, what we have is just the Fisher information. And Fisher information, you can read more about it in this reference, but Fisher information just describe the underlying distribution. Like if it's a Gaussian, then I have a sigma and a mu, or a mean and a standard deviation. That's all what I have. So what we are really kind of just looking at this kind of Fisher information is the surprise that led us to this this big statement in this case in here. At inference, given a single image from a single class, again, that's what I spent the last 20 minutes or so just to kind of set up this issue that at the inference, at deployment, I have a single image from a single class, and then what do I have? What information? What we are trying to convince you is that we can extract information about other classes, right? And the motivation behind making such a statement is that the gradients, right? So the Fisher information, as I will show you in the next slide, is nothing but really kind of describing the gradients. So the gradients, when you say, I have this input image and I'm really kind of inputting this as a model, I'm saying, okay, this is a cat, right? And there are, let's say, 10 other classes in there. Actually, the gradient is leading you to discard all the other classes. This discarding the other classes is information, right? And we are really trying to tap into this information. Can we quantify this information? Can we use this information? If I'm discarding the dog, I'm discarding the airplane, discarding the other classes, this discarding function has information in it. So can we extract that information from at the inference at deployment from a single image from a single class in here? So the derivation actually is done in this paper, but you can really do a variance decomposition of the Fisher information, and basically it will end up basically all what you have is just basically gradients, right? And the gradients in here are really draw information from underlying distribution as learned by the network weights. Okay, so this is just a case study, and that will show you how we obtain all of this. Again, you have this Bullmastiff image from ImageNet. You have the trained model. It basically says, and this is a dog in this case. In a way, what we're really doing, we take this X, we are projecting this on the manifold, right? And then if you apply just the GradCam, I will talk about this in a minute. This is the heat map you get, right? So what's happening in here? What's happening in here, when you input this in here, the features that really contributed to the model to make a decision, this is the dog in here, are really the ones that really go when you project this sample into the manifold, this you don't have access to everything, but you have access to this projection and the neighborhood, right? Actually, in that case, basically, it captured basically the snout, the jaws, the face as the main feature that will contribute to my decision to make this a dog. In this case, right? And this is just a case study of that. Right? Okay, so now we say, okay, now we have a single sample, we have a model, we have this projection to manifold, or the risk representation space to be more careful. Then now I have access to these kind of, this kind of local information in here, right? So this gradient provide this local information around the vicinity of X when it's projected onto this representation space, right? So all that's what the information I have. So now, yes, we can make a decision. We can look at heat maps, but now we have other information. The question becomes, where do I go from here in the manifold? right? Sorry, because you have this projection, and now you can really say, okay, now I'm at this. It doesn't matter. This sample is a correct sample, is a novel sample, is a noisy sample, is an attack. Nevertheless, I have a projection into this manifold. The information actually we can say, okay, now where do I go next, right? And the path where I go next, it has a lot of information that we can really use, and we'll show you in the remaining part of this presentation and tutorial how to use it. So we have, in this case, like we have 3 different paths, for example, and each one of these directions will give me this kind of, some kind of, an optimization that will give me some kind of information about what's really happening in this case. Okay, so part 2 and 3 of this tutorial, we'll talk about basically, for example, counterfactual. Can I really make up like X prime? Right? Can I really make a counterfactual, input, and then can see how the manifold has to change itself to include this X prime into its own space, right? That information, how much the model is really have to include this, is the gradient, right? But also is extremely rich in information and utilization. And later on, we'll talk about basically the interventions. Given this fact in here, you can just have the projection. Can I start to really play around with some kind of made up interventions, but they are not really made up for no purpose, with a really very good purpose. And Mohit will talk about that in part 4 of this tutorial. So with that, what I'm hoping at this stage, I'm convincing you with is you have a single sample, you have a model at the inference. Now, when you really project this into the representation space, then there is a gradient at the inference. The gradient does not really change the model. We are not changing the model but we have a lot of information that we can obtain from the gradient at the inference to do a lot of different things, right? And again, the underlying hypothesis that basically if you have a single sample from a single class, you already have information about all the other classes just because of the gradient calculation at that stage. And now when you say gradients, you can just think of it as gradient in the last layer, or you can even basically go all the way back. So you can have intermediate layer, early layer, and how you use them. We'll show you different examples in the tutorial how you can utilize these. So the first case studies will use this kind of knowledge is an explainability at the inference. So we'll start with visual explanations, what they are, what they mean. We look at the gradient-based explanations, introduce the GradCam, kind of a de facto explanation method, and how can we use this GradCam to give us basically what we were talking about, this kind of interventions that I mentioned earlier. And then we'll talk about case study and introspective learning. Okay, so most of the content in the next, I would say maybe 15 minutes or so is really coming from this paper in the Signal Processing magazine. And you can just scan the code to access the paper if you're interested in this. Okay, so let's look at this. What are explanations? Explanations, by definition, are a set of rationale used to understand the reasoning behind a decision, right? If these rationale or a set of rationale are really visuals, then we can call them visual explanations. As an example, I showed you this bull mastiff early on. In this case, the class is bull mastiff. We have a dog, bull mastiff. We have a cat, kind of background, and so on. And then these are real explanation maps. We have these kind of real maps that we obtained, right? And now it depends on what you are looking for. Are you looking for observed correlations? Are you looking at counterfactual? Are you looking at contrastive? Then you can get this heat map. And the heat map in this part of the talk is, if I have this kind of red and dark red, that means I'm using these features as the highest priority in making this decision. As I'm going into the green and then the blue, that means basically this important features. Right? So in this case, if you look on here, why bull mastiff, it's basically because of the snout and the face, basically more or less in this case. And then we'll talk about the other ones. But before I talk about how what this means at the remaining ones, it's really important to talk about how explanations in here, they provide just not only explaining the decision, but they really provide context and relevance. And I will explain what we mean by that. So imagine that I have this okay. So I have this spoonbill image as an input. I have this model in here, and then the decision is a spoonbill. So it's correct. So it's a good decision. But now the explanations basically they really serve a purpose, right? So if a kid like in elementary school comes asking the question, why is this a spoon pill, right? So the heat map that we obtained, and this is the real heat maps that is obtained from the code, is really highlighting the body of the spoon pill mainly, so really pink, and you can really translate the heat map into language, say pink and round body, and basically straight peak, because it's listed, after this, and here we have the peak, basically is kind of highlighted next. So in this case, the kid really learned a little bit or learned about spoon pill. So in this case, we can say the explainability in this case it served the purpose of explaining the decision done by the network. Now, if you have an expert in the field, the expert now is really having questions of fine-grained questions, right? Questions of the form of why spoon pill rather than a flamingo, right? What the heat map actually gave us, and we'll show you how we obtained these. So the code actually came back with this heat map. And you look at this heat map in here, it really highlighted the neck. So it really highlighted the neck, that basically the difference between a spoon pill and a flamingo is the S-shaped neck compared to the straight neck, right? It's really pinpoint exactly to that difference mainly, right? As the main reason, right? So in this case in here, the experts say, okay, that's a good thing. It's really good that the model figured out the difference between a spoon pill and a flamingo, although it really missed the legs, right? Because that's the difference between the two birds. But it's really the neck shape and the length of the legs, right? So in this case, the expert will say, will gauge how much it should trust, basically, or we should trust this model, because it really pinpoint the S shape compared to the the S shape neck compared to the straight neck, but it really missed the legs, right? So in this case, there is a purpose of the explanation to assist the model, the effort data in this case. And maybe somebody else will come and say, okay, it's a fox, and then they kind of ask questions of almost irrelevant in this case. Why spoon pill rather than a fox, right? What the code gave us back, the explanation from the code is almost highlighting everything in the body, like the pink body shape, the neck, the beak, everything. So everything is different from a fox, right? So in this case, okay, that's good. The model is not being tricked basically to differentiate between fox and the bear. So there is some kind of a trust in this case, right? So all of these really kind of make us claim that explanations can provide context and relevance, right? And where this is really coming from, they're really coming from not only from the model, how it's trained, but also from our own questions. Again, as I mentioned earlier on about the point prompt, we're really prompting the baseball bat that I showed you earlier on, right? The humans are really kind of prompting. And it's sometimes the human thing that you're really doing a good job by prompting, but the performance actually is giving worse. In this case, the way we are really asking the questions, right? It will really provide relevance. So it's relevant to me as a user, to me as somebody who's asking the questions, although the model hasn't changed. So it's the same model throughout all of these. So there is a purpose for explanations way beyond just explaining the decision, but it's really providing context and relevance in this scenario. So now I'll spend some time to talk about how we can really get these heat maps, right? So the visual explanations, one of the early methods that we have seen, one of the early methods that was deployed to get explanations. You get an input image like this, and then you start to have a batch, like to mask out certain part of the image. You have this is an elephant, and then you mask this part in here. You get 0.95 probability of being an elephant in this case. You can repeat this again, but now you move the mask, the head of the elephant, the animal, and the probability actually dropped from 95 to 75, right? So basically this is, so what people have been doing is just taking this mask, and then on the upper left corner, and keep sliding it, right? And every time you slide it, you have probability, and now you have a heat map, right? You get a heat map like this one, right? So of course, if you have 1 million pixels, then you are doing this, but 1 million times. Right? It's very, very expensive. Mm-hmm. However, it's really very, very important and very interesting to notice that although the model was trained on image labels, right? Not localization, image labels. However, it really kind of, you can see there is a localization element to it, right? And that's really very, very insightful, very, very interesting. The same thing for the go-kart in here. It's kind of figure out basically there's a go-kart in the front in here, and then in the back there's also, and the same thing. It really captured this using this method in here. So this was very insightful. That means visual explanation really can tell you, more fine grained about what's really happening in the model, way beyond just what was trained on for image classes. So people start to okay, now what can we do and how can we obtain these? The less expensive, because if you input this 1 million times for this image, then that can be very, very expensive, and you cannot do it at deployment anyway. So this is where basically we have this gradient methods came into the picture. So this paper in here can really kind of talk about these methods. So we have an input image, you have your output, and then you start to backpropagate all the way to the input space, all the gradients, and this is what we refer to as vanilla gradient. And as you can see in here, it's very, very noisy. There is some kind of things happening where the cat is, but it's not really very clear, not very clean. It's very, very noisy in this case. So, authors came back and said, okay, now we really kind of look to, backpropagate only the positive gradients. Right? So we just look at the positive ones, and that's what the convolutional gradient map is. So you can see there is an improvement. There is a localization for the cat eyes in here. And then basically, finally, we have the guided backpropagation, meaning that you take whatever you have from this method in here, but you only backpropagate with the positive activation. That's all with backpropagate in this case. And you can see it's much, much less noisy. There is much more localization. You see the face of the cat in here with the eyes. You see a little bit about maybe the legs in here, a little bit of the tail. But it's much less noisy. So this is really very, very good. So all of these basically were early methods in trying to obtain visual explanations until we got to the GradCam, and the GradCam has been a de facto visual explanations for a while. But in a nutshell, in the GradCam, and we have the paper cited in here if you are interested in looking at this in much more detail. Basically, what you do is basically you input to the model. You look at basically the last layer in here. You backpropagate the last layer. And then if you have, let's say, we have 6 activation maps in this case, basically you do a really kind of, pooling. And then now you scale each one of these activation maps with these alphas. Right? So that's what you obtain. Basically, this is kind of weighted activation map at the last layer only. You input this to a ReLU, and then you basically size to the input image. This is the heat map. You overlay this heat map on the input image, and that will just give you the heat map of the GradCam. What I really want to pinpoint is basically what we are backpropagating is the prediction class, or the predicted class, YC in this case. Right? It's a dog. We are backpropagating a dog in this case. And here, and that will tell us, that's where the idea that this heat map in here is explaining to us why did you label this as a YC or a dog or a bull mastiff in this case. Right? So that's basically why the Y bull mastiff is really kind of the question for this heat map. In their paper, they showed basically can do this for many different applications, captioning, VQA, and so on, and the list goes on if you're interested in that. So now, what's really important to us within this tutorial is back to this, what I showed you earlier. Right? What I just showed you in the GradCam is this heat map. So it's really kind of, you obtain, you input this, you look at this, backpropagate the bull mastiff, the correct class. You look at the last layer, you do the GradCam operations, and then you overlay the heat map on top of the image, and this is what you get. Now you can say this is an answer to YP or Y bull mastiff in this case, and it makes sense. Like it's looking at the face and snout and so on in the dog or the bull mastiff. But now the same thing is the question becomes, can we really use the same thing GradCam to answer questions of this form? Like again, back to this intervention that I was talking about. Imagine that my intervention is more like, what if bull mastiff was not in the image, right? So I would like to look at the model and see if what the model will look at next. Remove the bull mastiff, right? And then basically look at what the model is looking at in the image. In this case, and I will show you now how we obtain this, is looking at the cat, which makes sense. Like if the dog is not there, then the model is looking at the cat, and this is the heat map image. Then I can go even further and start to say, okay, why bull mastiff rather than a boxer? Like two different breeds of dogs, and we're trying to kind of figure out if the model basically can tell the difference between them. And this is really a real heat map we get back. You can see basically it's much more localized on the jaws of the dog, but it really pinpoints the difference between the two breeds of dogs is the jaws basically the dog, which is really amazing, right? Again, there is some confusion with the cat, right? And also it makes sense. The cat is there, it adds some confusion. In our paper in here, the signal processing magazine paper, we have a whole basic kind of discussion about these kind of three forms of questions. It's all what you need to have a full explanation. The questions of observed correlation form, observed counterfactual form, and observed contrastive form. They are of the form of YP, Y if not P, then YP rather than Q. So these are the three types of questions. So the first one here, Y-ball massive, we will use the GradCam as it is. Right? That's what it is. We are backpropagating the correct class. So now, how can we obtain the heat map for the second question and third question? For the second question, the question is just to remind you, what if ball massive was not in the image, right? So now, this is exactly the same as what we have in the GradCam, but what we are really backpropagating in this case is the negative, right? Especially the negation of the gradient, right? That's the only change we are really doing for the GradCam. Everything is the same. So we add a negative sign in front of this gradients in here, and the rest of that will give us the heat map that I just showed you in this map. So as if the ball massive was not in the image in this case. Now we can also backpropagate, the contrast between two classes, P and Q. Ball mastiff and boxer in this case, for example, or in this case, the cross entropy. To backpropagate basically the difference between these two, and you backpropagate and you get the heat map that I showed you earlier on. And this is the power of these methods. These questions in here are all obtained from the same basic kind of code. It's with a very small change in what we are backpropagating. And the more details in the paper. But let me talk about the results. Right. So let me look at this in here. What I have an input image. I have 4 of them. From the spoonbill you have seen before, I have the ball mastiff, don't turn left, and then I think it's a Bugatti in this case, car. And then this is the GradCam, right? The GradCam, as we agreed, is Y spoonbill, Y ball mastiff, Y don't turn left. And you can see from these heat maps, like if you look at the spoonbill, we already know that is the body. If you look at the ball mastiff, is the face. Don't turn left. It's looking at this kind of where you have this kind of line in the middle and then the arrow on the left. Just looking at the right things. And for the cars, you can at the front of the car is kind of the main reason why it's hiding on this class of the car. Okay, so that's all GradCam. And now the next and the third column, I have contrast one. So I have these images. I'm trying to contrast these images with the input image. I'm trying to contrast the flamingo with the spoonbill, the boxer with the bull mastiff, don't turn right with the don't turn left, and I don't know with this car, with this car with that car, right? So I'm trying to look at these two. This is convertible, I believe. I cannot see from this side, but this is convertible. This one is not convertible. So, okay. So now I'm using the same method that I had here, right? I'm just contrasting and backpropagating, same thing as I showed you earlier. And this is the heat map I obtained here. So we saw this one before, the neck shape is compared to straight. In the bull mastiff, basically, is the jaws, some confusion with the cat. Don't turn right, don't turn left. Basically, highlight this difference in here. You can see basically there is something different, this region here, and the lines in here. So that to us, that makes really sense. The same thing between a convertible car and the car is the top of the car is the kind of the main reason. So these things in here, we can say basically, we as humans, we accept these. It makes sense to us. Not perfect, but they make sense. We can interpret these. We say, okay, that's it matches what we would have contrasted ourselves to the two classes. Right? Let's look at these two cases in here, like these ones. So the first one is this one. We are looking contrast. So the next column is the contrast 2. That means images. We're contrasting again with the first input images. So now we are contrasting basically, like let's look at this case in here. Contrasting this bird with the bull mastiff, right? What you notice in here, if you look at the heat map coming from the contrastive questions, right? It matches exactly the GradCam, right? It's almost perfect match between the two, right? The same thing in here, totally different car. And if you look at the heat map we get, or it's almost like matches what we obtained from the GradCam. Why? Because these are really kind of completely different class, just like the fox and the spoonbill earlier. Like the fox is very similar, right? But now, if you look carefully at the next one, this one here, like I'm contrasting a sub sign with don't turn left, right? So now we as humans, if I ask you why don't turn left rather than a stop sign. And then the questions or the answer that could have come to your mind is that I don't really have the letters ST, O, and P, right? I don't have the word. That's the main reason, right? If you're asking a human being, the difference between a stop sign and don't turn left, maybe ST, O, P, maybe it's because all red. But if you look in here, the model came back and says this part. See this part in here, the lower left corner? That is the main reason, basically, where the model decided that this is really the contrast between a stop sign and don't turn left, right? And again, my classes, I tell my students that the way we are optimizing these networks, we are really trying to make them lazy. We'd like to find the shortest path to make a decision to make a, right? In this case, what happens is, if you look carefully at our traffic sign dataset, and all the traffic signs that we have, all of them, with a lot of variations among all of these in point of view and distortions and scale. But these are the main, traffic signs that we have in there. If you look at them all carefully, the only one that has any kind of this kind of line in the lower left corner of the sign is the stop sign. So what the model did, found basically the only difference between these two is this kind of line there. That will characterize the stop sign compared to all the other traffic signs, right? And it made the decision, and it's captured that, right? So it didn't really do something wrong. Like it really did what it's supposed to do. It found the difference between these traffic signs. It turned out to be this one. But do you really trust this model? Right? So the difference between don't turn left and stop sign is this line, because somebody can just come and just draw with a marker a line on the lower left corner of any traffic sign, and they will think it's a stop sign. Right? It's very easy to trick this model. So the role of explanation here is the kind of is really very, very important in this case. Again, I want to go back to this message in here that we said earlier, that we mentioned that basically kind of the discarding this kind of information is done through the gradients, right? And the contrastive explanations provide such a case study. Remember that you have contrast between a spoonbill and flamingo, right? And basically that kind of discarding information is really happening when you do this contrastive explanations. So if you have spoonbill as an input, the answer of why spoonbill, basically you look at these features in this case, but also when you input, when you start to contrast between the two, spoonbill and a flamingo, then you are really looking at these features basically in here to figure out basically the neck is the main feature. So I'm discarding all the other features because the neck is really the main one that differentiates between these two in here. Okay, so I'm hoping by now we start to kind of convince you that gradient and inference can be extremely useful. We find a way to extract this knowledge to give us a complete visual explanation sets using YP rather than Q, Y not P. It's kind of 3 sets of explanations. And now I want to use all of this into a case study, what we refer to as introspective learning that showed up in Europe's paper 2022. And this is a 2-stage inference in neural networks. You can scan the code if you are interested in finding the paper in here. Okay, so look at this. I mean, in the old days, I mean, I think all of us who have been teaching for a while, we used this many years ago, right? I mean, I show this to my students and say, can you tell the difference between a puppy and a muffin? Right? In the old days, basically the models could not differentiate between a puppy and the muffin, like before 2019. But I mean, now they can. But it's very scary, right? I mean, you cannot differentiate between a puppy and a muffin, right? So while you were looking at this, like when I asked you the question, can you tell the difference between a puppy and a muffin? In your brain, basically, and this is something computational neuroscientists, I mean, they really know a lot about this, more than me. Basically, you are really introspecting. You start kind of, you have visual cues coming from the image. And then your brain, you start to ask questions. You start to ask questions to yourself without you knowing it, right? And your brain is doing that for you. And say, okay, is this a blueberry, or this is the eye, or like, and the location of them, and basically, is this the edge of the muffin, or this is really the face of the puppy? So all these introspection questions you are asking, your brain is asking, your brain is doing this in no time to tell you, to give you basically kind of the ability to differentiate between a muffin and a puppy, right? And the list of questions can be, can be extensive. So now this actually motivated us and inspired us to look at this. Can I create an introspection, basically kind of, network? In this case, we can split this into two parts. The first one, we had the visual sense. You sense basically the features. Again, the spoonbill, you have the body, you have the beak, you have all these different things. That's sensing. And then once I have that, can I have a reflection stage? A reflection stage where I start to ask questions, right? And these questions, hopefully, will really kind of make my solution more robust, right? And will make me more confident, more robust. I'm hoping to get, I have more, a true confidence in my decision, more robustness, more generalization, and the list can go on, right? And you can see this in here. The reflection questions could be of the form what we have seen before, right? You can say, why is spoonbill rather than flamingo? Why is spoonbill rather than crane? Why is spoonbill rather than pig, and so on? And the list can go on. And then again, I have an output, y tilde in this case. We had an output early on, so this is from the previous model, y. And I'm hoping that basically y tilde in here, it's more generalizable, it's more trust in it, it's more confident, it's more robust, and less correlation error. So we can really formulate this into a problem statement, is that I would like to simulate introspection into neural network, right? And by definition, we define introspection as answers to logical and target questions. Again, you have to be logical, but also you have to be targeted, because they're targeting to really kind of, to look at the final grain difference between different things, right? And you can say, basically, what are these possible target questions? Already we showed you this earlier. And we showed this, especially these target questions are the same one we use for visual explanation. It's the same ones. Why P rather than Q, why not P, and so on. Okay. So that in mind, we can go a little bit into kind of more technical definition in this case. So in here, introspection answers questions of the form YP rather than Q, YP, where P is a network prediction and Q is the introspection class, right? I would like to kind of, have a contrast between P and Q in this case. So given a network f of x, we have a data sample x, and the network prediction is y tilde. Introspection in f is the measurement of change induced in the network parameters when a label Q is introduced as the label. So what this means is I have an input image x sample, I have an output y, right? And now what I'm telling the model is label this basically y with something else. Like, it's a spoonbill, but I would like you to attach a flamingo label to it, right? Or a pig or something completely different, right? And now what if you are really measuring the gradient, right? That means how much the model has to change itself, right? To accommodate this new label to this sample, right? And now when we say, somebody will say, okay, that change, maybe activations. Activations give you almost like a distance, but gradients give you distance and direction, more or less. So it's much more knowledge into the gradients than just the activations in this case. So that's why the gradient at the inference can be extremely useful in here, like to measure how much the existing model I am deploying in real time will have to change itself to accommodate a new label for this sample, which already knows the prediction label for, right? And you can really scale this to many different things. So we have to go into the details. You can look at the details of this into the paper, but it's just to show you that really the well-trained network, the gradients are really sparse and very informative. So when you say Y5 rather than, for MNIST, Y5 rather than, this is very shallow network, I think a couple of convolution layers, Y5 rather than 0, you can see this is really it's showing up only for the 5 and the 0. So it's very, very sparse representation. What's more important is this. So if you do Taylor series decomposition on the contrast between I have the introspection class yi, and then I have this is the gradient, right, with respect to the weights, and then I have the y hat in this case, which is the prediction class. So now I'm looking at the difference. I'm looking at the contrast between these two. If you apply a Taylor series expansion and the details in this paper, in the Neuros paper, then what you get these two terms. So in one term, you look at the yi, the introspection class, in this case, the flamingo, for example, and then the prediction class, which is the spoonbill in this case. So now, in order to really make a change, so if you only have this prediction class, imagine that you don't really have this contrastive. You just have basically what you will have on the right-hand side, only the y hat or the prediction class, right? Then it's very easy to change in the input space to trick you, right? To trick basically what's really happening in the gradients. But now, not only you have to change in order basically to make this trick or to make this challenge, you have to change the input class, but also you have to change the relationship between this y hat and the yi. So the relationship between the introspection class and the prediction class, the relationship between them has to also be manipulated in order to trick the model, right? And that is not an easy thing to do. It's very, very tough. It's one thing to trick the input model at Gaussian, make it, trick that, and then try to change all the relationship between the input class and all the other n-1 classes. Right? It's very, very much harder to do that. Now, this is just a graphical way to illustrate what we do in this case. How can we really build this this kind of introspection? Again, not go into the details. Basically, you have a model as it is before. What we do, in reality, have this introspection. What we have in here, if you have n classes, right? You have an input class. Basically, what you will backpropagate all the other n-1 classes. So one backpropagation is okay, the second class like 0, 1, 0, 0, 0. The next one 0, 0, 1, 0, 0, and so on. You backpropagate these, right? So you backpropagate n-1 times, right? What Mohit actually showed in his paper in here is that actually you don't really have to do n-1 backpropagation. You can do backpropagation of a vector of all ones. They are equivalent. And mathematically, we have that in the paper derivation, the paper. So what we do is this introspection element that we do. You have your trained network. You basically input an x. You backpropagate vector of all ones. You collect all these gradients in here, right? And then basically in this case, you normalize and you vectorize this. So now what we have created, the gradients at the inference become a feature. Right? So you input the sample, backpropagate a class of all ones, a vector of all ones, collect the gradient in the last layer, right? Normalize and vectorize. This becomes a feature. You can keep doing that basically for all different samples, right? For every single sample, you have such a feature vector, right? So now you have for x1, for x2, for x3, you have this gradient as a feature vector. And then you can really train a very short, very shallow or very simple MLP model in here, right? So now what we have in here is what we call like the visual sensing, which is really the trained model given to us. Then we add to it introspection, right? Introspection and reflection MLP, right? And now what we are hoping for, what we get out from this MLP in here, right? Or the only difference between this y hat and the original y coming out from here is basically this MLP in here, where the input are the gradient as feature vector, as I explained earlier. So let's look at how the performance in here changes. So let's look at this case. In here, how we define robustness, right? So basically, it's generalizable. So the model really has a generalization feature to it. And then, we increase accuracy on alt distribution data in this case. At the same time, we have a calibration. Because the calibration reduces the difference between the prediction accuracy and confidence. And I'll show this in a minute. So what I will be showing you is two data sets, Cypher 10C, where you have different distortions. Each one have, I think, 5 different levels. What we have on the right-hand side is our QTSR data set, traffic signs. Also, we have, I think, 17 different distortions. We have 5 different levels. So mild all the way to severe for each one of them. So these are recognition data sets. So I just want one comment about the calibration issue. So for shallow, what we have, just focus on this plot in here, the lower left corner. And in a nutshell, for shallow network, for example, the difference between my prediction accuracy and my confidence, right? That's basically what really calibration error is, right? The deeper the network is, the higher the gap, right? So the higher the gap, that means the higher what? The calibration. There is a big gap between my confidence and my prediction, right? So this is not a good thing, right? So and usually for a deeper network, you will have this gap higher and higher. Now, what we did on these data sets, these ones, we apply this method in here, right? we obtain first the performance from the trained model as it is, and then we look at what happens to the performance by looking at the y tilde, by adding this reflection introspection stage afterward. Right? So look at this on the left-hand side. The left-hand side for the Cipher10C dataset. The one on the right-hand side, Cipher10 and Q dataset together in here. Let's focus on the one on the left-hand side. So let's look at this in the red kind of hue for points in here. These reflect to, or they are for ResNet 18, ResNet 34, ResNet 50, and ResNet 101. Right? So what we have in here on the x-axis, expected calibration error, and the y-axis we have the accuracy or performance in terms of accuracy. What usually where we'd like to be is a low calibration error. Means there is a small gap between my confidence and my prediction. So I'd like to be here on the x-axis, the low x-axis. I want to be very high on the accuracy. So I'd like to be in the upper left corner. So when we apply these models as they are on the Cipher10C dataset, we obtain these 4 performances in here across the testing dataset, the testing data in this case. Now, after we apply the second stage, which is the reflection, the introspection stage, right? And these are really covered by they are depicted by the green hue in this case. All of them move to the left to the right. I'm sorry, to the left and to the top. All of these points, right? Not only that, so the accuracy improved a little bit, on average 4%. But what's really fascinating that the calibration error improved by 42%. So I reduced basically the gap between my confidence and my prediction by 42% on average between these points. Which all of them move to the left and the top in this case, which is what we are really desiring. And the same thing happened in the other experiments where we have the Cipher10Q dataset. These are the traffic sign, and this one we have what we did, we looked at what are the common distortions between the 2 datasets, the 5 different levels, and we put them as one data. And then we have a trained model, and then we test on the testing data in this case. So this is before introspection, right? And then after introspection, all of these performance has moved to the left and to the top, and on average 4% accuracy improvement. But what's really more important is the 42% in calibration error improvement. Again, we did this basically for robustness techniques. This comparison of all these ones. If you look at the Argomax, this is kind of one of the best ones in this case. We didn't really have much change or drop in the accuracy. However, the calibration error improved by 40% compared to the Argomax in this case. And in the paper, we have a lot of different applications. I can go through just very quickly. The ones on the left-hand side. If you are really familiar with the image quality assessment, basically when you have image quality assessment, how good the quality of an image is given. We have PSNR is the default one. Then we have all these different methods in here, and then we have the unique one is the unsupervised one. It's unsupervised, basically there's ground truth, and it really has been kind of doing extremely well on most of these data sets, multi and TID 13. And then when we add the introspection to this unique one, always there is improvement, not only in the performance, but also in the calibration in this case. So that's really very, very promising for image quality assessment. For active learning, for those who really familiar with active learning, you're deploying and then you have a new sample and then you decide, I want to take this sample to the human annotator, I will annotate. So you have to make a decision when to pick these samples to be annotated, and then including the training and keep doing that. So there's quite a bit of literature on the active learning. Whenever we add this introspection piece to it, there's across the board improvement in the active learning case. And finally, in the out of distribution detection, so these are different methods in here. Look at these papers; it's very, very tiny. But whenever we add that very simple step of reflection after the model, there is an improvement in OED, out distribution method, across the board in here. I'll leave the rest. We have many different applications on the GitHub code and the paper if you're interested in this. So before I finish this part, something I really want to highlight in here is that we train a model for a certain task, And then we use that model for that task. In reality, as most of us, if not all of us, we know, the model learned much more than that task. The model really learned a lot about the data, much more than that task, right? So, and what we are hoping that we convince the community, and I'm hoping that we start to convince you this morning that one way to extract that knowledge from the trained model is through gradients. And we show that for explanations, we show that for generalization, robustness, and name it. It's just a simple basic kind of back-to-back filter of all ones at the reflection MLP stage. You really improve your robustness by a huge margin. And nothing really changes in the model itself in here. And then Mohit later on will talk about after the break is you can really go into I just showed you the last layer, right? Or what I showed you in the last layer. But he will show you examples where you go into the earlier layers as well. And then now the question becomes how can you extract these gradients from these layers? So I'm hoping that this becomes something that we can really use where there's a lot to be done at the inference stage, and gradients is our tool to do that. Before we go to the break, there is this task if you are bored in the break and you would like to do something. So it's a break between 9:30 and 10. So we work on subsurface imaging. Right? This is for earthquake, geothermal, CO2 capturing and storage, name it. And one of the main things is when people really kind of look at these subsurface faults. Faults is basically when you have the earth layers, start to kind of extract from each other. That's where something extremely important for earthquakes, for geothermal, for CO2 capture, for oil and gas is very, very important. For 70 years, people used this faults for oil and gas extraction. Now they are using it for CO2 based kind of storage, right? And geothermal, predictions, performance prediction. So now, what we could do in here, we have this tool where we deploy it publicly, and between experts from geophysics and between a normal crowdsourced human being, go and really kind of label these faults in here. And you will see, basically, it sounds simple, but once you start doing it, you will start to ask questions, just like the reflection one, many questions. Is this a fault, or is this just a noise, right, as in the image itself? So hopefully some of you will be able to play with this one a little bit in the break. So we'll be back at 10 o'clock. If you have any questions, I think we have 5 minutes for questions, and then we can break out for a break and then come back at 10. Any questions?
10:15.
Oh, 10:15. Okay, sorry. Thank you. 10:15. Okay, we're back at 10:15 then.
Yeah, officially, I think it's 10:15.
Okay. Yep. Okay. 10:15. I'll not take your break time from you. 10:15. We'll be back here. Yeah. Any questions before we leave? Yes.
Maybe I missed it, but it wasn't mentioning the loss functions for the pairs.
It's cost entropy in that case. That's what we are using. Yes, it's a cost entropy. Yeah. P and Q.
Do you ever try different loss functions? And do you have interesting results with choosing different?
We did. Yes. Yeah.
In the appendix of that paper, we have got 10 different loss functions for the results.
Yeah.
I think L1 loss played well, L2 L1 loss.
Okay. Other question? Okay, thank you. We'll see you at 10:15. Do I stop recording?
Yep.
All right, I think we can start now. So from now on, we'll do parts 3, 4, and 5, 3 of which are going to be part 3 will be uncertainty, part 4 will be intervenability, and we'll just conclude in part 5. So just before we went to the break, we left you this small piece of food for thought kind of a thing, kind of an introduction into what will be uncertainty. It's a topic that is very near and dear to my heart, mainly because it is so frustrating. It's so impossible to actually work on and so difficult to work on. And every one of you will probably have a different definition of what uncertainty is going to be. But hopefully over the next hour or so, I'll just go through and talk different kinds of methods, explain certain terminologies, basics of it, and so on. Right. So just before we left on this slide, I think Professor Ghassan was talking about you give someone and a person who does not know anything about subsurface imaging, you give that person an image of the subsurface and ask them to label a fault. We did this for 26 different people. All of them had different results. So if I show them this one image, here we are just showcasing a result of like 5 people. This is how they labeled the faults. They had to go in and do the actual labeling part. And as you can see, every single column is different from each other. And this tells you that the results it's sometimes very hard. And in many cases, we talk about this kind of image classification when we talk about machine learning and deep learning algorithms. But in real world scenarios, in some aspects of where machine learning is required, the labeling itself is not easy to do, in which case, when there is no good labels, well, there is going to be something called uncertainty. And that is a good segue to our part 3, which is going to be about uncertainty at inference. We'll talk about a few things here. We'll just talk from a very high level perspective of what uncertainty is in classification, and some methods that go through it. And similarly to last time, we just have a couple of case studies where we'll talk through a couple of results with an uncertainty framework. All right, I always like to start with this particular slide just to showcase what uncertainty is. For me, I know that a few years back, it was a much simpler time. This meme was everywhere. If I look at this meme, if I look at the 2 images on the left-hand side, I see a white and gold dress. This is just me. I always see a white and gold dress. Even when I know the fact that that dress is blue and black, it does not matter to me. My eyes still see white and gold instead of blue and black. And this I know is a perceptual anomaly. I know that I should be uncertain about what I'm seeing about my eyes, but that does not matter to me. I still see it as white and gold. So essentially what uncertainty is it's a model knowing that it does not know. So in this particular case, I am the model. I know for a fact what the color of the dress is, but it does not matter to me. I see it the way I see it. I perceive it the way I perceive it. And that is where the uncertainty is going to come in. So let's go a little bit more technical into defining what uncertainty is going to be. This is a nice example. If you're coming from a signal processing background, every one of us knows what a cosine signal is. If I was to reconstruct a cosine wave, it's pretty straightforward. It's just cos 2 pi ft plus some phase phi. Let's say that there is a small error within this uncertainty framework, and that error manifests itself within the frequency. Right? And if you go through the formula, you'll see that while the real signal without noise is this black one here, with a small amount of noise added, there's a lot of error that is involved within this particular signal when you're trying to reconstruct it. And this error can sometimes lead to very big problems if you're using it in an important system. So this is one kind of an error or an uncertainty that can come into picture. That is because there is a problem with the data itself. The frequency of the data has noise, and that is what we would call the first one. We call it aleatoric uncertainty. The second source of uncertainty is that as an engineer, I have done the wrong thing. I should have taken a cosine function with the phase. So it should have been cos 2 pi ft plus pi, some phase that I should have added. But let's say I'm still in my first year. I've never heard of what phase is. I do not take a phase in my signal reconstruction. What happens in that case is there's this kind of a noise that is involved. The model I have chosen to construct my sinusoid is incorrect. That is where another type of uncertainty comes into picture. That is called epistemic uncertainty, which you see in this part. So when it comes to machine learning and deep learning algorithms, the way we try to study uncertainty is by decomposing it into its sources. The source can come from the data itself, which is aleatoric, or it could come from my choice of models. So in a way, you can say that if I had chosen AlexNet, the answer would have been something. If I chose a Swin transformer, the answer would have been something. Your choice of which model you're using has introduced the uncertainty, which is the epistemic uncertainty in that particular case. Right. So this is like from a source of uncertainty, but what a neural network should give us is given by this kind of a visualization. Pretty common example here on the left-hand side. This is an autonomous driving setting. You have, as you can see, a few cars. There's a bus on the right-hand side, plants, trees, and stuff. What you see in the middle is a neural network output from a segmentation. What you see in most cases, you can say that the purple is road, it's pretty good. The blue here is a car, pretty good. The green is the foliage, also pretty good. But just, I want you to concentrate on this part of the bus here. Hopefully you can see my cursor here. We know by the basic fact of how transport and vehicles are, that you don't have this kind of an irregular shape when it comes to the edge of a bus. Like this should not exist. So that should tell me that there is some mistake that the network has made in this particular case, which is where the uncertainty is going to come into picture. And this is a heat map of how this uncertainty must look like. And this is where the uncertainty heat map is coming from. Ideally, whenever we think of neural network outputs, we think we want the right prediction, which is the middle portion here. But as we saw, when it comes to novel data, noisy data, robust data, out of distribution data, sometimes a network has not learned something. And in order to account for this not learning something, it has to give out something other and more than just the prediction. And that is where the uncertainty part that is here on the right comes into picture. I want to expand on what I just said a little bit more, going back to an example that we had earlier. So let's say the same stop sign. So if you were here in the first part of the lecture, of the tutorial, I think Professor Ghassan had shown you this nice example of how contrastive explanations work with the stop sign and no stop sign detection, right? So an algorithm, a deep neural network, tries to take the easiest route by looking at the bottom left corner. If there is some kind of a line segment in the bottom left corner, it knows it's a stop sign, because among the 14 different traffic signs, there's only one class that has this kind of a bottom left line segment. Now, if I am during inference, I'm giving a nice, it's part of the training distribution stop sign to a network. It needs to tell me that the class it belongs to is a stop sign. It needs to tell me with a confidence of 98% and with an uncertainty of 0.1%. Let me just say that there is some quantification of uncertainty. This is what the uncertainty quantification is, which is 0.1%. Confidence in this case, let's just consider it to be softmax confidence. Right? So in this situation, what is happening is that a network has looked at the bottom left corner, seen that there is this kind of a line segment, and given me my class and everything. However, there is another traffic sign, a go traffic sign, which coincidentally is exactly opposite of what you need to do when there is a stop sign. But this go sign was not part of my data set. It's a novel class. It's a new class that a network is seeing at inference. It has the same characteristic, which is that at the bottom left corner, there is a line segment. Right? So when a network looks at this go sign and the only thing it knows is that at the bottom left corner, there's a line segment, hence you need to classify it as stop sign. This is what it is going to give me. It's going to tell me that the class is stop sign with a 98% confidence and uncertainty is 0.1%. So what I want you to take out from this is two things. One, confidence and uncertainty are not the same thing. Both of them are, in this case, 98%, 0.1%, but there could be very well, and there should be algorithms where you need to get a confidence of 98% and probably another uncertainty of 98% as well. And the second and more important part is what these two algorithms need to give you, right? So let's say the network has not seen the go sign, but is shown this at inference. And setup, a neural network setup or a deep learning setup with no inferential uncertainty estimation will probably give you 0.1%. But at inference, ideally, if it is equipped with some kind of an uncertainty setup, it needs to give an uncertainty quantification of 98% while maintaining the same kind of confidence. Because again, we are talking about at inference. You cannot go in and change the fact that you need to add another weight. Instead of 10 classes, you need to add 11 classes at your outputs. That is not something that is possible, right? So instead, what you would need to do is you cannot change the fact that it will not be a stop sign. Rather, you need to make sure that there is some other quantification that tells you that you should not use this output, that you should probably revert back control back to the driver and so on. So this is uncertainty quantification setup, which is going to ideally give you this kind of 98%. I hope this part is clear, the difference between confidence and uncertainty. Whenever we talk about this, there's always a lot of confusion regarding some of the terminologies. So this slide basically just lists a few things, which is constantly, we keep referring to this, and in many cases, myself included, we just conflate all of them with the other. Sometimes when I say probability, I probably should have said confidence. Sometimes when I said confidence, it should have been uncertainty. Because we use all these terminologies so colloquially in English, sometimes we make mistakes in how they are presented. I just want to quickly take a couple of minutes to go through what the terminologies mean. The first one, probability, very simple. It's a vector of something between 0 and 1, all of which add up to 1. So I'm sure every one of us has used something like a softmax confidence, softmax probability. That gives you a probability vector. Logits from the output of a neural network passes through a softmax layer. You'll get a set of probability vectors. Confidence in non-conformal settings is just the argmax of this probability. So let's say I have, in the previous examples, we saw something like 98% stop sign, and let's say it was 0.5% of no left sign. So confidence in this case will be the 98%, which belongs to the stop sign. There is an entire field called conformal uncertainty and conformal predictions, where confidence in this particular case is not a point estimate, it's not just the argmax, but rather another vector. Basically, it is a distribution. But in this tutorial, we're just looking at point estimates, where we are looking only at these kind of point estimate, non-conformal settings, where we have point estimates as our confidence. Likelihood, and this is probably the one that is most confused with confidence and probability. Likelihood in Bayesian settings refer to how the model is fit on top of the data. Probability is how the data is being perceived by the model. But likelihood is the opposite. It's how good the model has been fit on top of the data. If the likelihood is usually in reference to something like, let's say, AlexNet or Sven transformer, the likelihood that AlexNet will be able to work on my data distribution, if it's 95%, and likelihood of something like a Sven transformer will work on my data distribution is 98%. That tells me something not about the data, but about the model itself. And this is a very important distinction that we have to make regarding probability and likelihood, because the next one, uncertainty, is more similar to likelihood than it is to probability. It is a probability vector, but what uncertainty tells us is how well my model is. It tells me, showcases the goodness or the non-goodness of how my model will work on my data distribution. Right? And this is a very important distinction that we have to make. In other words, one way to think about it is that in my previous example, confidence looks at the bottom left corner line segment and makes the assertion that it is 98% probability that it's a stop sign, while uncertainty looks at the fact that there is green feature and there is the letters G and O to make the assertion that it's uncertain 98% for the same stop sign. So different features are being used in order to satisfy the class that it is a stop sign. And this is an important distinction. I hope it is clear. If you have any questions, you're more than welcome to just stop me and ask me in the middle itself. But this here is probability distribution formed from feature outputs that showcase non-goodness of data, while probability is going to be the goodness of the model, which in this case was the line segment at the bottom left corner. In many cases, the last word here, calibration, it's conflated with that of uncertainty. A well-calibrated model has low uncertainty, is generally what we say, but they're not the same thing. Calibration is a dataset dependent metric. That is, I cannot calculate the calibration of a single sample. So when we talk about during deployment, we have an unknown model and a single sample. You cannot talk about the calibration for that. Calibration only exists if you have 100,000 samples, and you can construct that accuracy and that probability across different samples. If it's a single sample, you need to have an uncertainty estimate. But more than that, if you have a data set, you can go ahead and have this kind of calibration. All right, so these are like very common terminologies that we use, and in many cases confuse all of them with each other. But it's very important to know the distinction about all of them. All right, so let's talk about what the challenges in uncertainty quantification are. There's a very simple and a very important challenge within uncertainty quantification, which is that the primary purpose of whatever model we are using is its primary purpose does not go hand in hand with uncertainty quantification. So we saw this part in, before, where you have a neural network. All required information kind of collapses into the final layer. You're getting a single number, which is your logits. And this logit is going to tell you that your output belongs to that of a dog. So both these two dogs will be considered as dogs at the end of the day, right? Their attributes, which basically is that the dog at the bottom, it's an angry dog, does not matter, while the dog at the top is looking for a belly rub, does not matter. Angry dog and happy dog will collapse to the same thing, which is a dog. Let's say, and that is where the uncertainty aspect comes in, where let's say I have two classes here, cat and a dog. Dog is given by triangles and cat is circles. If my goal is to classify something as a dog, I'm better off with the image on the left-hand side. I want all my triangles to conglomerate here in one part of my graph, while all the circles I want to conglomerate in the other part of the graph. So what this tells me is that all dogs, doesn't matter if it's an angry one or a happy one, wants to collapse to the same point, which is that of a dog. And this happens because, when you train, you're back propagating this one hot vector, 1, 0, 0, for an angry dog, as well as a, the happy dog, right? So the network has done what it needs to do, which is collapse it into a single point, but there's no difference between all the triangles here, so there's no uncertainty. In other words, we say that features have not been preserved, and the actual techniques for these are called preservation techniques, and in this case, no preservation. If you want some kind of a preservation to happen, this is what it's going to look like here on the right-hand side. But unfortunately, if you want to preserve some kind of intra-class distance, this can be detrimental for the performance itself. So your dog, ideally this triangle here should have been on the left-hand side, similar to here, but you see that it's now on the right-hand side. So it is going to be incorrectly classified, which is going to cause a performance drop. So there are a lot of uncertainty estimation algorithms or uncertainty quantification algorithms that are used during train time, where you're preserving certain distances. It's called spectral distance preservation. Many of them work well in terms of uncertainty quantification, but when it comes to performance, there is a huge drop-off that happens. So again, what we are trying to say is that it is better if you try to handle these things at inference rather than if you try to handle them during the training phases. So this is like a primary challenge within uncertainty estimation. I want to very quickly go through some simple uncertainty estimation techniques. The simplest one, and the one if you've worked on uncertainty quantification, there are certain ground truths almost that you use. There's no true ground truth for uncertainty. You estimate certain measures and use them as some kind of a ground truth. And one of them is generally this thing called negative log likelihood. Likelihood, as a terminology we defined before, is how likely is your model fitting the data. It's a better likelihood of your model fitting the data. Well done. There's not as much uncertainty. Generally, we use a negative of likelihood to measure uncertainty, because likelihood and uncertainty have an inverse estimate, but negative likelihood and uncertainty have a positive estimate. So lower the negative likelihood, lower the uncertainty, right? This comes in from Bayesian settings, with the central thesis being that negative log likelihood measures fit of a model by looking at all output logits. The issue in this particular setting, while using negative log likelihood, is that you require a ground truth. Now, you can use this when you're testing your model, but it requires ground truth to measure what your likelihood is going to be. And many times during inference, it's substituted with that of prediction. Another very simple measure which does not require ground truth during inference is the idea of hypothesis margin. So hypothesis margin basically says that, maybe I'll just explain using the image here. So let's say I have an image, a data point X. In my representation space, it says that, okay, the nearest hypothesis is the inner circle here. Let's say this is class 1, the outer circle represents class 2. It projects itself closest to the inner circle. Hence, a deep neural network is going to predict that it belongs to the inner circle class. Hypothesis margin finds the distance between the existing class prediction and the nearest class, which is not the prediction, right? Or in other words, it's the next most likely class prediction. So this is basically your hypothesis margin. So it's commonly used to rank the difficulty of these kinds of unlabeled samples. In active learning, this is a very famous measure for using this. The thesis for using hypothesis margin is that during training, networks implicitly learn the difference between classes and find features that maximize the difference. So during training itself, you have constructed these inner circle and outer circles in a way that it understands the difference. So if this were the flamingo and spoonbill example from before, it understands that there is a difference between the neck, and it's and that is the difference between these two hypotheses, the flamingo and the spoonbill. So the pros, of course, is that no need for ground truth at inference. The cons is that you require a complex network. And the last one is very important because we'll differentiate between old networks like AlexNet versus the newer networks like transformers. And the main difference is going to be the last point here, which is a requirement of this complex network. Ideally, the network should have learned the implicit difference between these hypotheses in order to construct a good margin. Again, we are talking about inference, right? So it has already trained for these differences. All right, so these are simple uncertainty quantification. This was well known before 2010. Negative log likelihood, even back from 1950s, there's something called scoring roots and proper scoring roots within statistics. It was used from that time in order to construct these kinds of uncertainty estimates. But when it comes to deep learning, there's been a lot more work that has been done when it comes to uncertainty. And probably the work that most comes close to defining uncertainty in deep learning is this paper in 2017 called Ensembles. So the idea is this. So what exactly is uncertainty? The fact is that deep learning, when you train it, on the same data, you are going to get different models. You might get the same output. So in this case, let's say I have trained n different models. I pass a cat image through it. I am going to get a cat as the output in all of these scenarios. And yet, as you can see, the value is going to be different. Here it is probably more than 50%. Here it's at 50%. Here it's less than 50%. Right? And the distribution is basically different in all these scenarios as well. So a variance or an entropy of these distributions is what uncertainty output is going to look like. So from a deep learning perspective, this is the most intuitive and simplest explanation. Network, if you're trained it multiple times on the same data, even though it is giving you the same accuracy, the distribution of its outputs are different. So variance across these distributions is giving you some kind of an uncertainty measure, right? But again, let's take big foundational models these days. You have 65 terabytes of data in the Common Crawl dataset. How many of these networks, how many GPT 4.5s can you actually train and then find what the differences of outputs is going to be? It's not simple. It's not easy to do computationally these kind of things, constructing these ensembles. So there has been a little bit more research that has gone on to construct more simpler, or at least computationally simpler ways of constructing uncertainty. The first one is something called Monte Carlo dropout. So dropout, the idea of dropout was introduced in 2013 from Google. It was used as a regularization technique. The goal in dropout is very simple. 20% of the time, let's say you drop your neurons and try to estimate your outputs based on the remaining 80% in the first epoch. In the second epoch, randomly again drop 20% of your neurons and see what you can get out of the 80%. So in a way, you're regularizing your network during training in order to construct a better solution or a better set of parameters. What this paper did back in 2016 was use dropout, a trained network, use dropout at inference. Back in 2013, when Google first constructed dropout, they only used it during training, then said that at testing, you shouldn't use dropout, you should get what the prediction is. But in 2016, this paper suggested, okay, let's use dropout during testing as well. What that means is that if you forward pass the same image n different times through a network having, let's say, 20% dropout, at each forward pass, you're going to get a different neural network because of the fact that you have randomly dropped out 20%, right? So in a way, you're simulating this kind of an ensemble setup using a smaller set, using just a single network. During test time, you're basically dropping out, let's say 20% or 30% of your neurons to get your solution. And that is going to give me, so let's say a single forward pass is going to give me n logits here. Sorry, this should have been t forward passes for the next slide. So let's call this as t forward passes with n logits, where n is the number of your classes. So the number of columns here, number of rows here, sorry, is going to be t, and the number of columns is going to be n, where the n logits is giving you different classes. The way you would now understand how to get your uncertainty is quite straightforward. This is the formula, and we tend to try to reduce the number of formulae in the tutorial. This formula looks hard, but it's in fact very straightforward. I'll take this and I'll use the previous slide in order to explain this. We have already seen two definitions of uncertainty based on source. One is the epistemic and another is the aleatoric. Just as a reminder, aleatoric is for data and epistemic is for the model. The way you calculate aleatoric is softmax of your logits, which is f w cap of t of x. Take the entropy of that and then take mean across t. In other words, each row here, I'm going to take the entropy of my row. So each row will have one number, and I'll take the average of all those things. That is essentially what my aleatoric uncertainty is telling me. Right? So if I were to repeat that, I have single model. This model has n different forward passes, t different forward passes with n logits. What happens is the output distribution of a particular logit. So in this case, these things, I take the entropy of this entire thing, and across the t different architectures, I am going to take an average across all, which is the aleatoric. Predictive uncertainty is I take the entropy outside. So I take the mean of everything, and then I take the entropy outside. So in a way, if I were to look at this image again, if I take entropy in the horizontal direction, it's going to be aleatoric. If I take entropy in the vertical direction, it is going to be predictive uncertainty. Right? Those are the only two differences in this particular case. And another way of looking at this formula is that if I take this negative sign, if I put it on the left-hand side, aleatoric plus epistemic is something called a predictive uncertainty. So even if you're not interested in decomposing into data and aleatoric uncertainty, if you take a mean of all of your outputs and take the entropy, that basically is your predictive uncertainty. And that is something that we will be using from now on. Right? So this is a very famous example or a method of obtaining uncertainty called Monte Carlo dropout. Of course, there is still an issue with using Monte Carlo dropout. The issue being that if I use 20% or 10% MC dropout during training, I need to use the same output right now as well. I need to use the same dropout during inference as well. And empirically, it has been shown that that is not very good. We want a dropout of 0.1 or 0.2 when it comes to training, but when it comes to testing, you want a much higher dropout, 40% or 50%. But unfortunately, you won't have both of these things. You cannot have very high dropout initially during training and a high dropout during inference. You need to make sure that that number is exactly the same. And also another important factor is that depending on the kind of data set that you're using, it's very, your MC dropout has to change both during training and during your inference. So there's a lot of hyperparameters you need to tune, a lot of experiments that you need to do to make sure that the output you're getting is the true, it's reflecting the true kind of uncertainty. But of course, this is computationally, again, it's much better than the ensembles. So there's ensembles. The next one is something like iterative uncertainty quantification, but it also has its own issues. The next type, big type of methods is something called single pass methods of uncertainty quantification. This essentially states that, let's say I have a pseudo representation of my manifold. Let me just construct a distance across the pseudo representation of manifolds. And this paper, the method itself was called DUQ. They use a Gaussian process in order to model during training. Or have some kind of validation set as well during inference, and then construct some kind of a distance that would tell you how far away from your manifold your data point was, and use it as an uncertainty measure. But of course, based on the fact that we initially established that we cannot have any kind of a validation set or training set, right? When we are constructing these kind of uncertainty estimation techniques, it's not always possible to use methods like DUQ or other uncertainty estimation, single pass uncertainty estimation techniques. So what we are leading towards is similar to what we talked about before, which is how we can use gradients in order to construct these uncertainty estimation techniques. So gradient estimates come under something similar to the single pass uncertainty estimates, rather than either the iterative or the ensemble estimation techniques. And we'll talk about a little bit more of this in a couple of the case studies. One thing I want to say before going into the case studies is that uncertainty in many ways, the reason I started by saying uncertainty is is almost like a frustrating topic. The word itself can be used in any and all applications. I'm certain that if you go through all these applications, if you go through many of these, the papers and many of these applications, you will hear the word uncertainty somewhere or the other. And in many cases, the definition of each of these uncertainties is going to be very different. And again, you can pause it down to the fact that, uncertainty is such a word that we use so easily in English that sometimes without even our technical knowledge, we just kind of use it. And that is a big issue, in fact. But it's very relevant at deployment because we want to provide a specific uncertainty measure that objectively allows users to trust this kind of neural network estimation. All right, so this brings us to this idea of inferential machine learning. So this was already shown before in the first part in explainability. We have a lot of knowledge that a neural network is trained, but whenever we think of neural networks, we are utilizing it for what it was trained for. But the goal of inferential machine learning is to transmute this knowledge somehow in order to make sure that it works in many other situations, right? And what we are positing and putting forward today is that the way to transmute that knowledge is via something called gradients, gradients at inference. We saw two case studies already, the explainability one and noise robustness one. We have results for all of these applications. In fact, auto distribution also we saw already, but there's a better result that I'll show you now. We will talk about two things, and we'll talk about two more case studies. One is misprediction detection, and within that, in fact, we'll talk about auto distribution and adversarial detection as well. And another case study is going to be about uncertainty visualization in this particular case. So this is a newer paper regarding uncertainty gradient-based quantification of prediction trust within neural networks. Again, the case study that we are looking at is misprediction detection. So in this particular case, our main goal or our main output is going to be that gradients provide some kind of a distance measure. And this shouldn't be very surprising, because when we talk about training, gradients is something that we already use in order to construct this kind of a distance measure, right? But the difference is during training, we had access to something called an L, a loss function that we used in order to construct our neural network. The issue currently that we face at inference is that we don't have that loss function. You can, of course, choose a loss function, but it doesn't matter because you don't have 50,000 data points in order to train your manifold and your distribution. So we need to come up with a new loss function, a new way to construct a loss function, and consequently the gradient as well. And in a way, we have already seen this happen. When we talk about the contrastive explanations, what we did was we backpropagated Q1, Q2, Qn. In the introspective learning stage, we backpropagated n different classes to construct all these different explanations. What that means is we were looking at what change was required in a neural network in order to incorporate this new data point, in order to incorporate this new knowledge or information that the output belongs to a different class, in this case, a contrastive class, right? So we can backpropagate all these contrast classes as one hot vector, as n one-hot vectors that we saw in introspective learning, and higher the distance, higher the uncertainty score in this particular case. Right, so if I were to give a similar manifold kind of an example, let's say x and x dash, if I were to backpropagate a contrast class 1 instead of the prediction class, there needs to be this kind of a difference. There needs to be this kind of a change within the manifold. If I were to give a different contrast class n, there needs to be a higher difference or a higher contrast class or higher energy that it needs to take into consideration in order to put this within the manifold, right? And in a way, I've stated this here. So gradients provide the necessary change in manifold that would predict the novel data correctly. I use it correctly in quotes because we know that it's not in fact correct, it's in fact incorrect. When we ask the question, why spoonbill rather than flamingo, I know that it's not a flamingo, and yet I ask that question, why spoonbill, not a flamingo? When I ask the question, why spoonbill and not a chair, I know it's not a chair, and yet I ask the question, why it's not a chair. But I'm forcing a network to ask itself the same question. If it were to make that change, what is the amount of required change in order to construct, in order to change its manifold, essentially, is what these gradients are giving. So if I were to give that example here, so how much change is required within the data to predict an incorrect class? Larger the required change, larger the trust. I hope this statement is clearer. So if you want a neural network to change its prediction, if it requires a large amount of change, then that means that its initial prediction is correct, or it believes very strongly in its initial prediction, right? So that means that the distance where the network data point is projecting onto the network is much higher for a different class than it is to the present class. So in this particular case, you have your network, you pass a spoonbill in, it says it's a spoonbill, you ask why spoonbill. The physical meaning of incorrect class backpropagation is this, the neck here. If I had asked why spoonbill rather than fox, then everything would have been highlighted, right? So that means it requires a much higher change to incorporate the fact that it's a fox than it is a flamingo. And that is exactly what this image is showing you. The distance between the blue data point and the representation space is much higher when, let's say, something like a fox versus it's something like a flamingo. And this tells you something. The fact that it's closer to a flamingo than it is to a fox tells you something about what this data point is and what uncertainty it has. So if I were to go through the method, it's very similar to the introspective learning part, at least the first stage. I have my network, I pass it through the network, I take the final fully connected layer gradients, I normalize and vectorize them. So the first part is exactly the same. In introspective learning, what we did was construct a network out of it. But now I'm going to create a measure out of it. Right? My goal right now is not to create another network, but rather to create some kind of a metric called grad trust, where it's going to be variance of gradients of predicted class divided by mean of variance of gradients. There's a lot of theory behind this, which is in the paper. Essentially, the theory goes back to the idea of Fisher information, except this time, instead of Fisher information of the likelihood, we are looking at the Fisher information of the loss. And Fisher information of the loss is telling us how much change, the sensitivity, how much change is required, how much this change tells me about the parameter itself, rather than the likelihood about the parameter. And this grad trust is giving you that kind of a measure. So the top k counterfactuals are based on predictions. So let's say if I have ImageNet, which I'll show you results on, if it's 1,000 different classes, I'm going to be using 100 classes. Top k, which is the top 100 classes, in order to construct this measure. So gradients are obtained by backpropagating loss between the predicted class and itself in the numerator, which is the loss between the prediction and itself, and the denominator is going to be a predicted class and all the other classes, which is essentially going to be the flamingo, right? So if I were to go back to this, basically what I'm looking at is how confident it is in its prediction divided by how confident it is in what it needs to change to incorporate new predictions and so on. It's a very simple measure. And these kind of gradient measures exist in literature. There's something called grad norm, which came out in 2020. The difference between grad norm and this measure is that you take, in grad norm, what you do is take the L1 norm when you backpropagate the KL divergence. Here, what we are doing instead of the L1 norm, we are taking the variance of these gradients, variance of the energy of these gradients in this particular case. And I think the backpropagation is done not as KL divergence, but as a cross entropy loss, which is very, very similar. So this is like the block diagram for this kind of a setup. Again, the first part is similar when it comes to the introspective learning. The next part is we take the energy variance and we normalize it based on all the counterfactual classes. All right, as I said, this particular setup, we are using it for misprediction detection. And I want to take a couple of minutes to explain what misprediction detection is. before we move on to other applications. And I'll do so while talking about the evaluation methodology itself. So the idea of misprediction detection is simple. Let's say I have 50,000 images in my validation set, and 50,000 is coming from ImageNet. My goal is to say which of these images are classified correctly and which of them have been mispredicted. And that's the misprediction detection. This is how I do it. I go via I go to PyTorch and I look at all available neural networks that have been trained on ImageNet dataset. I run inference across all 50,000 images and I'll obtain all different measures of uncertainty. Now, the different measures are shown here. I hope it's big enough to read it, but essentially there is grad trust. The second one is confidence, which is softmax confidence. Essentially what this means is I pass my image through a neural network, then I take the R max of my probabilities, and that is the confidence. Next one is margin, which is the hypothesis margin, NLL, negative no log likelihood that we talked about. Entropy, which is a simple statistical measure, P log P. Odin is an out of distribution detector. We're using this because it's also a gradient-based method. Purview and grad norm are two other gradient-based methods. Purview uses gradients across all layers and it takes in the energy of the gradients. Grad norm uses only the last layer and takes in energy of the gradients. The difference between grad trust and the two at the bottom is that grad trust is using variance and normalizing it based on the loss across different classes. All right, so what I do is I get all these measures, and for each trust score, I order the images in an ascending order. So that means I have 50,000 images. Let's say I'm using something like grad trust. I'm using grad trust goes from 0 to 1,000, let's say. So I'm looking at the numbers within the grad trust for each image and arranging them in this kind of an ascending fashion. And for a given percentile, I'm looking at the accuracy above that percentile. So let me talk about what the x-axis here is. So let's say at percentile 0. What this means is that I'm looking at all 100% of my 50,000 images. So across all 50,000 images, what my accuracy is. I believe this graph is taken from AlexNet. So that accuracy is around 65, 66%. This is the top one accuracy for ImageNet validation set. 10 percentile essentially means that I'm taking out the 10% of the bottom placed grad trust images. So across 50,000, I take out 5,000. So among the remaining 45,000, what is the accuracy? So what this means is that I've taken out the least trustworthy images out of my validation set. And in the remaining ones, my accuracy is now around 78%. And it has increased significantly. Right? Compare that to the next best one, which is margin. Hypothesis margin, what it has done is it has also taken out 5,000 images away out of the 50,000, but it has done according to its calculation of what the trust score, which is the margin, is. And its accuracy is around 74% of the 45,000 remaining ones. Same thing you can do for all the other trust measures. At 20%, what it means is that you have taken out 10,000 images. So among the 40,000 images, grad trust is around 90%. Right now, I believe here, hypothesis margin is close to 80. NLL is kind of catching up with 76, 77%. And you see that NLL outperforms margin very quickly. Right? So this is essentially what we are doing. We can calculate the accuracy after every percentile, or we can calculate the F1 score after every percentile. And we'll have two measures called AUAC and AUFC. We do this across a large number of ImageNet trained classifiers on PyTorch. And we're showing you the results here. I know there's a lot of numbers, and I just want to concentrate on a couple of conclusions in this particular case. Let's look at the rows. All the rows are ordered based on accuracy. AlexNet has an accuracy of 65%, while MaxVIT has an accuracy of 82, 83%, I believe. So that means that everything in between, all the other networks, all the other rows here are in between these two things. There are two trends that I want you to notice. One is how NLL is behaving and how margin is behaving. If a number is in boldface, that means it's top two. As you can see, grad trust is almost always in the top two performing, except in the 89.1 here. Everywhere else, it is in the top two performing, and mostly it is the top performing. But usually the second one, at least initially when it comes to convolutional neural networks, is that NLL was very good in terms of doing misprediction detection. Margin was not as good. But as you can see later, margin has become much better compared to NLL. Now, this goes back to something that I was talking about when we discussed these simple measures between margin and NLL, right? Margin requires that your network has already learned the complex characteristics within your data set. So it knows the difference between a spoonbill and flamingo. Is this a shape neck? So it can actually quantify that margin well. So a higher capacity network, so something like transformer architectures, max VIT, spin transformer, vision transformers, are much better if you are doing some kind of an uncertainty quantification. You would rather use margin-based metrics than you would NLL-based metrics. GradTrust kind of combines these two metrics, and there's a lot of theory behind why that goes, why that is the case. The fact is that we are using a loss function in our negative log likelihood and then back propagating it, and that loss function is where the margin actually is, and it's that basically is why you see that GradTrust maintains this performance across both CNNs in the beginning and the transformers at the very end as well. Right? But this is an important statement because whenever we use uncertainty definitions and we try to quantify uncertainty, many times NLL is used as the ground truth. So if you see the famous Monte Carlo dropout paper from 2016, 2017, you see the results. It's compared against NLL, and we look at the correlation between NLL and Monte Carlo dropout to say if one is better than the other. And that probably was good when it comes to CNN architectures. But you should not do that now with the better architectures. If you're using some kind of transformer architectures, you should probably not be using something like NLL in order to do uncertainty quantification. Margin is better, and something like GradTrust is better. Again, this is for the application of misprediction detection within the same setup. I want to show you a few qualitative examples as well. So on the left-hand side, yes. Sorry?
All the models trained in a supervised fashion?
Yes, all the models are trained in a supervised fashion. We have results on unsupervised as well. So we have M2 encoder and a couple of other contrasted search supervised learning methods. The same, you'll find the same kind of setup in that case as well. Margin is better than NLL in that case as well. Sorry, whenever possible, I'm just gonna try to take a few swigs of water. So, all right, so I wanted to showcase a couple of things in terms of the qualitative results. So in terms of qualitative results, I want to show softmax confidence versus GradTrust. Softmax confidence, by the way, it might seem like softmax is not doing good, and I'm speaking against it. There is one very important quality within softmax that does not exist across all the others. So there's about how many? 9 different metrics here. The only bounded metric is softmax confidence. Confidence. In other words, this is the only one that goes between 0 and 1, while all the other metrics is not bounded. It can go with a much higher or lower. GradTrust, for instance, goes from 0 to 800, 0 to 1000. There's no maximum involved over there. Right? So softmax is, even though it may not be a good uncertainty measure, it is a good confidence measure and something that could be useful in many other occasions as well. That being said, we have softmax here on the y-axis, GradTrust here on the x-axis. Every single point, 50,000 images, the GradTrust and softmax scores that are being put in this particular image. Green means that the prediction was correct. Red means that the prediction is incorrect. What you'll notice is that most of the bottom left corner here means that they're all red, which means that they have low trust and low confidence, and rightfully so, they have been mispredicted. Those on the top right corner, most of them have a high confidence and high GradTrust, and they have all been correctly classified. The more interesting facet here is the ones in box 2 that we have presented here. We have shown 2 images qualitatively, 4 images, 2 of which are mispredicted, and 2 of them are correct predictions. One of the mispredictions here has been intentionally blurred because you could see the faces. But behind this, hopefully you can still make out there is a limousine prediction. There's a limousine behind this, right? And the true class for this particular image was supposed to be a limousine. My network told me that it's a picket fence, which is obviously incorrect. But it did so with a very high confidence. As you can see, softmax confidence is about like 95%. So this is very similar to the stop sign and go sign that I was talking about earlier, right? So it's saying that it's a picket fence, but it's saying so with a very high confidence of 95%. Ideally, we should not be using that confidence in order to make any downstream application task. What we should use is the trust some kind of an uncertainty measure? As you can see, the trust for this, if it's in this box, it's very low. It's the bottom 20% or something like that, right? So this is incorrect. A very interesting example is the one here. This image, I don't know how easily you can see this, but it's basically that of a stage. It's an orchestra. So there is a horn that is shown here on the screen. In other words, what this means is that both horn and stage belong. So it's something called co-occurring classes within ImageNet. And there's a lot of examples within ImageNet that has something like this. So the network predicted it as a stage. Even though it is correct, unfortunately, whoever has labeled this image said that it's a horn, right? So your network was forced to make this wrong decision. So my softmax confidence is still telling me that it's the stage with 95% confidence, with very high confidence. It's in this box, right? But my grad trust is telling me, just hold on a second. It could be a stage, but there's also an image of a horn. So it could be a horn as well. So because of this co-occurring classes, there has to be uncertainty that is involved in your decision-making process. There needs to be a confidence, and there has to be a corresponding uncertainty as well. And this is something that we see across different architectures, across different results. Another very nice observation that we got out of this is that when it comes to AlexNet, low grad trust is due to co-occurring classes. So the horn and stage we saw before, this one, pill bottle and bottle cap. These two are literally the same kind of class. They're co-occurring in this particular case. While in transformers, the trustworthy aspect, the problem with trust in transformers is due to class resolution. So in this particular case, is it a laptop or is it a notebook computer? It honestly depends on the person that you're asking. Very similar to the fault example that we gave at the very beginning. You ask one person, they'll say it's a laptop. You ask another person, they'll say it's a notebook computer. More people you sample, you'll probably get a 50% of both the things. So your confidence should not be high. All these cases, by the way, the network very, very confidently said that it was a notebook computer or stage and so on. It should have a high uncertainty associated with this setting, right? And these are some very important assessments. These are very important conclusions that we want to draw from this setup. Now, I'm running a little bit out of time, so I do need to move on. But again, if anybody has any questions, you're more than welcome to just stop me here. So the next set of experiments we want to talk about is this idea of out-of-distribution detection. So this particular images we saw during the introspective learning part. So there is this ImageNet C dataset. ImageNet C has about 3.75 million images. So what has happened is there's about 50,000 images that are taken in by sorry, this is the wrong citation here. So ImageNet C benchmarking neural networks for robustness. I think that is the name of the paper. So you can Google that for ImageNet C. So ImageNet C essentially takes 50,000 images in the validation set. They add 15 different noise types. So Gaussian noise, short noise, impulse noise, and so on, and 5 different levels. So 15 multiplied by 5 multiplied by 50,000 is going to give you 3.75 million images. So there's 15 different challenges, decolorization codec, and so on. There's different validation as well, but we're not using that here. There's 5 progressively increasing levels in each challenge. So the goal is to, of course, recognize the 1,000 classes from ImageNet using pre-trained networks. And we are still using the same evaluation setup, it's almost like a misprediction detection setup. So we did this between MSP, NLL, margin, Odin, and grad trust. And in almost all cases, what you'll see is that grad trust performs much better than existing metrics. Mind you, Odin is an actual out of distribution setup. We also have this on grad norm as well, but grad norm performed even worse than Odin. So we put the better performing metric just for the fact that otherwise we couldn't fit all this in a single table. But essentially in almost all cases, except the red one here, 25.49, there's a 39, which is better with NLL. But essentially, in this case, have it in the notes. So the accuracy in ResNet 18 is in fact this 3.44%. So it was only 3% accuracy. So that's why it doesn't tell you too much. Across 50,000 images, you only have about 1,500 images across 3.75 million images, there's a very small percentage that was classified correctly. So you don't really get so much out of this number, 25.49. But in all the other ones, the accuracy is higher, and this kind of uncertainty metric has to be higher as well. So that was more from a corruption detection point of view. Now let's move to an OOD evaluation setup with natural adversaries. Now, if you're aware of adversarial images, it came out, the original paper came out in 2013, and then FJSM paper came out in 2014. Deep neural networks were doing extremely well and beat the human benchmark, or almost beating the human benchmark back then. But then adversarial images are these nicely engineered, crafted noise that if you add to a data point, an image, it completely derails your neural network prediction, right? Those are engineered adversarial examples. Back in 2021, there was a new paper, ImageNet A dataset that came out that introduced this kind of natural adversaries. So this image, right top corner, tells you the best. So if you have a dragonfly, so this image, you can see that there's a dragonfly, but if you look at the background, it kind of looks like a manhole cover, right? So and it's your network thinks so, at least. It thinks that this image does not belong to a dragonfly, but with 99% confidence, it says that it's a manhole cover. So there's about 7,500 of these images from ImageNet A dataset. And the goal in this particular setup, how ImageNet A is usually used, is you take 7,500 images from this dataset, 7,500 images randomly from normal ImageNet dataset, combined the two. And the goal of any detection algorithm is to select the ones that are out of distribution. Or you want to make sure that you know one is coming from ImageNet A, while the other one is from the validation set, which is the same training distribution as before. So we have results on this as well. And again, beating the same dead horse here, but essentially grad trust does better than the existing metric, and it is the top performing metric. In the paper, we also have it on video classification, and I think that was an even bigger network, S3D, MVIT, MVIT1, and MVIT2. So across all these methods, the simple measures of using these kind of counterfactual and contrastive gradients are better than using the prediction gradients and so on. Yes.
As I listen more to your I said that your grad trust is basically working still on activation maps or activation task activations basically. And this kind of suggests that this whole mixed prediction is more about misalignment between the actual explanation for the early prediction versus human explanation. Mm-hmm. Am I right about that?
Absolutely. So human explanation in this case is what the human being has said the output is going to be, which I think this correctly identifies what you're saying, right? So laptop or notebook computer. The human explanation can be either of those things here, versus the network is doomed to choose. That's one of the sentences we had used in the beginning. It has chosen the word laptop, it has chosen the word notebook computer in this particular case. Your GradCam or your any method is forced to show you why it's supposed to be a notebook computer. But then if you ask it, oh, can it be a laptop, or why could it be a laptop? So there is now this question of, okay, it could have been something else. And this kind of goes back to the stop sign and go sign I was talking about before. Your prediction has to work on the activation map, as you said. It needs to work on the fact that the bottom left corner is a line segment, while uncertainty should work on the green color of the go sign, and it should work on the letters G and go. It has to work on something other than the activation that was used for prediction. At the end of the day, we are still always limited to the fact that the network is predicting these activations, but it's discarding some information to predict these activations. And the discarding of that information is what feeds into, or should feed into, the uncertainty framework.
Follow-up question is that, would it be a more valid direction to actually focus on the models, class activations, to make it more promising the prediction, rather than just do a post-hoc trade to find the mispredictions? Because I think that it is more valuable a model that actually reflects explanation, its own explanation. Mm-hmm. And as far as I here is, if the model is still mispredicting something, yep, it's still into a misexplanation, let's say, yep, wrong explanation. You can just force a model or basically work on the model to make it more promising with its own explanation rather than just find misprediction after just.
You're right. So that is another branch of thinking, basically. where our goal is to make our network better and better, right? So that is essentially what you're leading to. And I do agree with you in most sense, but there is these idea of this novel data, this out of distribution data, noisy data. It's something that we cannot predict beforehand in order to include it within our training set or to make algorithms that work on this kind of data. We can construct better and better algorithms, but there will always come a time during inference where you will not be able to predict a particular situation. There is always going to be these kinds of novel situations. So the question is, at deployment, how do you identify them and how do you deal with them as the answer, right? So there is a limit that we will come to where your base network will not be better. But that is when you add a second stage, similar to the introspective learning framework that was talked about in this one. So that also is literally training a new network, right? So in that case, we were not just making a prediction, but we were taking the gradients across the 50,000 images in the training set and constructing a small 3-layer network to make a better, robust prediction, which is exactly, I think, what you were suggesting as well. So you want a better network to start with. That is absolutely right. But even with a better network, you're still going to have mispredictions, right? So in this particular case, we started with AlexNet in 2011. Swin Transformer, I think, was 2 years back. MaxVIT as well was a couple of years back. So across the 13 years, there has been a lot of work that has gone on in order to make sure that the 65% in AlexNet has now become 82% in MaxVIT. I'm talking about the top 1 accuracy. Top 5, I think, is 98% right now, but top 1 is still in the 82, 83%. More benchmarks that come out, more difficult it is going to be, right? And you'll never have this kind of an amazing method that will take care of everything, and you will have some problems at inference during deployment, and our goal is basically to say how you can overcome that issue.
Let's say in a critical scenario, like I'm a radiologist, and I find I don't know, infected bacteria in an image.
Yeah.
But wouldn't it be too late? And how am I supposed to work with that uncertainty measure that you provide? Your models provide. Is it too late to work?
Yeah, as a radiologist, you would have to then step in and you would have to say that the diagnosis from my automated learning system is incorrect and I need to make this particular change. And you take that data point, and there are methods like zero-shot learning algorithms that exist that now change your base architecture. There's a continual learning setup, online learning setup that now needs to change this kind of architecture that you can definitely do, that you should definitely do. But the measure that you need to use to say that there is a misdiagnosis is something that needs to come from the wrong architecture, in this case, the bad architecture, let's say, right? So for that, we need some kind of a measure. What we are saying that it should not be confidence, it should be uncertainty. That's, yeah. All right. So a lot of what we saw in the previous one is numbers. Numbers are great, of course, and we need them for papers, but at least for a tutorial setting, more for presentations. The better thing that we want to show are these kind of visualizations. So the next one I want to show is uncertainty visualization, and I'll kind of go against what we talked in the explainability section. Maybe not against it, but add to that explainability section. This is a newer paper in JSTSP. In fact, on IEEE it came out today, but it was accepted almost a year back, which is variance of induced contrastive explanations for quantifying uncertainty in interpretability. The idea is that the explanations that GradCam or anything else shows you is in fact incorrect, that there is some uncertainty that is involved with these kind of visual explanations, that visual explanations we say are explanations, but they're in fact not explanations. They are nothing more than just saliency maps from these kind of neural networks and large neural networks architecture. Given this kind of a Weibull massive, as you can see, the snout of the dog is not as highlighted as as other parts of the, let's say, the jowls and stuff. Why is that the case? Maybe that shouldn't be. Snout is an important part of the dog. So there has to be a certain uncertainty that is involved in this particular explanation. And our goal is to extract this uncertainty within explainability and show it to you. And at the end of this part, what I want to bring out is that uncertainty, that explainability is nothing more than uncertainty. You're just visualizing the uncertainty, and we are just calling it explainability. And again, I want to build up to it, but I just want to tell you beforehand that that is ideally what I want to show you by the end of this particular part. So there are many, I want to take a slight detour to talk about this, which is that there are many evaluation techniques for trying to say whether a particular evaluation explanation is better than the other. Let's take this one common example, which is called masking. Let's say I have an explanation. In this particular explanation, the red regions, let's say, are important while the blue regions are not. And I'm going to use that in order to make this kind of a mask. So essentially, this is where the red region would have been. This is where the blue region would have been. And I'm only concentrating on the region within the image that is important for making the decision. So SX1 is one explanation type. Let's say that is GradCam, while SX2 is another explanation type, which is GradCam++. And this is what it is giving me. Now, I mask my original image based on the explanations that I was given, and I pass it back through the trained model again. First SX1 with this kind of a masked image is going to give me a crane, while the second image is going to give me the second masked image is going to give me spoonbill, which is the correct explanation, which was the image explanation from before. So ideally now what has happened is that I'm looking at why the output given my masked image SX2, I'm seeing that across 50,000 different images, the expectation of y given SX2 is always going to be better than y given SX1. In other words, the second explanatory map is always performing better in terms of the output y given SX2 than y given SX1. And now I'll say, okay, if I mask my image based on the explanation and pass it through the network, it's always giving me the correct answer compared to the previous one. Maybe SX2 is correct. And I think this is quite an intuitive statement to me that SX2 is better than SX1 in this particular case, right? So let's hold on to this definition before. We will talk about evaluation later, but what is important here is this particular sentence: E of y given SX2 is greater than y given SX1. In other words, I select an explanation based on the fact that its expectation of output given my mask is better than any other explanation. Hold that thought. Let's say I'm using an ensemble technique or any other uncertainty estimation technique, Monte Carlo dropout. We saw earlier that what we are interested in is in this variance or entropy. In this case, we are looking at variance of y given this explanatory map. There's a very simple variance decomposition that we can use. For any variance, we can take it as variance of expectation plus expectation of variance, given y given s of x. In the previous slide, we just saw that we want to make sure that the expectation of y given sx is as high as possible. In other words, the variance of this number, which is expectation of y given sx, is going to be 0. For a well-trained network and an explanation that you have chosen, your variance of your output is always going to be spoonbill. It will not be anything else, right? So your explanation, you've made sure that the first term is 0. In other words, there is a lot of, in other words, if there's any uncertainty in my output, it is because of the second term here, which is expectation of variance given y given s of x, the output given your subset of your data. And this is a key observation, which is that uncertainty in explainability occurs due to all combination of features that the explanation did not attribute to the network's decision. Right? So the effect of a chosen intervention can be measured based on all the interventions that were not chosen within this neural network setup. In this case, interventions is an explanation of this context, but they can refer to human prompting as well. I'll show a result on the prompting that we saw in the very first slide. So what this means is that snout is not as highlighted as it is in the explanation, and snout is an important characteristic which is used to differentiate against other dogs, but hence there is uncertainty on why this feature is not included in this particular attribution. So this is what my uncertainty map is telling us in this particular case, that uncertainty in explainability, it occurs due to all the combination of features that were not chosen by this explanation setup or this intervention setup. But if I want to quantify this kind of variance, expectation of variance given y given s of x, what does this mean? That basically means that any and all interventions that were not taken, I need to take a variance across that. And that is interactable, right? Let's say I have a red in this pixel, I have red in this pixel. So that is going to be a different explanation than I have red in this pixel and I have red in this pixel. There can be an infinite number of these interventions about where these red regions might exist, where the important regions might exist. And again, this is where our definition of contrastive explanations is going to help us. We already have a way where we have y1 given as x1, y2 given as x2, y3 given as x3, and so on, right? So this is where I backpropagate the wrong class, the contrast class 1, contrast class 2, and so on. In other words, if I just take a variance, across all the contrastive explanations, that is going to give me my output, and that is your uncertainty. And again, I want to say exactly what I said regarding the go and stop sign. The stop sign, the go sign, your output needs to be based on the fact that there's a bottom left corner line segment, but the uncertainty has to come from the fact that the green was not observed in your stop sign. So the why stop rather than go, there has to be that the fact that green was not there, that will be incorporated within these contrastive explanations. And if you take an, like a variance across these explanations, the contrastive explanations, you'll be able to get this kind of an uncertainty within your explainability. You could do this against any kind of an algorithm that you're interested in, whether it's the transformers. So we have results on the same, the 14 different architectures. We can have the exact same thing in this particular case as well, and you'll be able to see the result. We also have this across SAM as well. So SAM, just to reiterate what was said in the first few slides, segment anything model, this cute cat, someone went in and they built 2 points. This is the inclusion point in green, and there's an exclusion point in red. The goal is to segment this particular cat. If someone has done this segmentation, the person has done this particular segmentation, you see this is how the uncertainty is going to look like. But this person did not get full 100% segmentation results, so they thought, okay, I can do much better. Maybe just having this point here is not a good idea. Let me just put 2 more points here. And this is the whole problem with over-prompting, right? So by putting 2 points here, the network now is very certain about this region. So just talking about the color coding here, if it's dark blue, then that means that there's no uncertainty. If it's brighter, then that means that there is uncertainty. So in this particular case, if you put 2 inclusion points in the hand of the cat, there is no uncertainty for the network at all. But less uncertainty in this region has meant more uncertainty in all the other regions. Now it's very confident that this is part of the cat, but it has now become less confident that all the others are not part of the cat. And that is what you see here. That originally there was a good segmentation, but now there is not a good segmentation. Right? And this is important. If you're using this kind of SAM architectures in these kind of foundation models within your workflows, it's not sufficient to show what the output is. You also need to show an additional amount of information. In this case, it is going to be the uncertainty framework, which is the voice framework, at least for this particular case. Again, we did the same. It's a very similar setup with SAM as well that we did with the previous results that we were showing. We can also, utilize this kind of a voice framework for GradCam and GradCam++ to compare between explanations or to compare between Swin transformer and VG16 and so on. So for instance, there's this very nice metric intersection of union that we can do so. I want to showcase a couple of examples here. Let's say I have this bald eagle. This particular bald eagle, it has been classified correctly as a bald eagle. What you see is the reason that GradCam is giving me is the base of the beak. Uncertainty is around the particular beak. GradCam++, on the other hand, it's showing you that the base of the beak is the same place where the uncertainty exists as well. Now, there's a philosophical debate here to be had. Should your network be uncertain about the same features that it used to make the explanation? If the answer is yes, I think that's a very valid answer as well. But empirically, what we have noticed is that once there are mispredictions, so if there are mispredictions in this particular case, the goal was to identify it as, I think, the snow dog, but I think it was identifying it as a snow port, which is basically why there is an explanation here. What you notice is that in this particular case, both the explanation and uncertainty are on the same features. So if that were the case, a network is shown to have mispredicted more. So across all the mispredictions on ImageNet, what we have noticed is that when uncertainty and explanation overlap, then that means that there is a higher chance of misprediction. While if they don't overlap, there is a lesser chance of misprediction, or it is a correct prediction. So it's a metric that you could use. But again, I think there is an argument to be made that your network should be uncertain about its explanations as well, which there might be some kind of metrics that showcase that fact. So this is intersection over union, which is a metric. I'm not showing numbers in this the tutorial, but the results exist in the paper. We have another metric, which is this idea of signal to noise ratio. So for the same bull mastiff image, we added a lot of noise in order to showcase the fact that when there is this kind of a misprediction and noise, both your explanation and uncertainty kind of becomes very noisy. So if you construct some measure like signal to noise ratio, what we have noticed is that during misprediction, your SNR is usually lower when compared to when there is some kind of a prediction. So you can still do this kind of a misprediction versus prediction attribute detection, but this time, not only are you giving a number, a metric, similar to GradTrust, but you're also visualizing what it looks like. And in many cases, like SAM, it is probably more important. Those kind of visualizations are more important to do than just numbers that you can give people. All right. So just very quickly, just a few memes to wrap up this particular part 3. Deep learning was working extremely well. 2013, 2014, adversarial images came into picture, and there's a lot of robustness issues that came up as well. And there's a lot of work currently that is going into making sure that things are more robust. While it works well with natural language data and natural image data, when it comes to more specialized data like subsurface images, biomedical images, things are a little bit more difficult. And this is one of my favorite things. We have done so much work on explanations and explainability that the first slide where we talked about the formula for variance decomposition, right? Whenever we are optimizing our explanation and saying that this is a better explanation than the other, what we are doing is in fact reducing the uncertainty. So instead of doing explanatory work, what we have till now been doing is just uncertainty work. So if there is some uncertainty in your output, that is what is being used in order to generate the explanations. When you're backpropagating your gradients with GradCam, if your logits were very high to begin with, and if the contrastive logits were very low, you wouldn't get an contrastive output at all. So the variance of them would be 0 essentially, right? If it's all belongs to the same GradCam class. So your explanation is in fact nothing more than an uncertainty. But again, this is more of an opinion, and there might be different opinions, which is equally valid. All right. With that, I'll come to the last part, which is intervenability at inference. Probably go a little bit faster in this particular case. Most of this particular part is dedicated to talking about, until this point, we have talked about how our goal is intervenability, or we want human beings to interact with these models and to make sure that these interactions are fairer and better, right? So when we talked about, you need to show these uncertainty algorithms, you need to show these explanatory algorithms. Interventions, on the other hand, could be negative as well. And the choice that researchers and engineers make affects this kind of interventions a lot. So before that, I just want to talk about these kind of definitions of intervenability. And there's no single definition, unfortunately, when it comes to intervenability. So we have multiple definitions listed here. So when it comes to causality, this is one where interventions are probably the most commonly used and have been used until this point. Once you have a trained model, you intervene on small factors within data to assess whether that particular factor is a causal or non-causal part. We assume that causal model exists. We assume that causal factors exist. And our goal is now to assess whether a particular factor is causal or non-causal. And to do that, we are doing some interventions. In a way, that is everything that we did in explainability research and uncertainty research as well. We just used a trained model. We did not, of course, make the assertion that it was a causal model, but we're just saying that its output is correct. That the spoonbill that we are getting out of it is correct, and it's doing for the right reasons. And then we are assessing whether those reasons are right. Has it taken an easy way out by looking at the bottom left corner and so on? And once you have that knowledge, you can go back and retrain it, or make the algorithm better and so on. Assurance when it comes to privacy is also very important. Machine learning is this huge aspect or huge field these days, where your goal is you have a trained model. You want to make sure that if there is some privacy related issue, you want to remove the data. You cannot just remove it from a data set. What you want to do is ensure that the knowledge is also removed, and that is where machine unlearning comes into the picture. And this is another aspect of intervenability. Interpretation also is another factor within intervenability. Once a model has explained itself, then you know that the model is doing something incorrect. Now you want to go back and make a model better. So instead of explanations being post hoc, there is a way that you can make, you can utilize these explanations as well. Introspective learning was one case, but there are multiple other algorithms that try to incorporate these explanations within interpretability. The actuation is basically amenability of neural networks, decision to human interventions. So interaction between these foundation models and users, like in SAM, for instance, right? It introduces an element of uncertainty. So till now, we have always thought that there are two sources of uncertainty. There's aleatoric uncertainty and epistemic uncertainty. There's also an out of distribution uncertainty, but there's certain facets of it which kind of are combined with an aleatoric and epistemic. But this kind of human uncertainty is right now very different than aleatoric and epistemic. A network may not have any uncertainty associated with how it has functioned, but as you saw in the prompting example before, humans try to put their knowledge and their reasoning onto a network. And if it has not been aligned to human reasoning, there is an uncertainty that is now involved. And this compounds by the fact that human beings keep trying to prompt, keep trying to get the results that they think that they should get, but they're not getting that particular output. The last one is to verify, and this is something that has always been used in intervenability. We have constructed large-scale data sets, whether it's ImageNetC, CureTSR, CureTSD data sets. We have added noise and interventions onto the original data to assess how robust or to verify how robust a particular neural network is. So all these 5 definitions of intervenability are valid, but it almost makes it sound like interventions are good and interventions are required. But for the next few slides, I want to say the opposite, which is that there are some kinds of negative interventions as well. And it's very important to take those into consideration. For instance, there's kind of a membership inference attacks. I think it came out in 2016, 2017, where the goal is you have some kind of a model that has been trained on some data record and class label. You have an attack model, which basically just tries to get the output, just tries to infer what the output is based on different combination of inputs, so that it can now recreate the database that was used for the construction of the model, for the training images itself. And this is a huge issue when it comes to biomedical images, when your data is ideally secure and differentiably private. The data might be, but the fact is that during inference, the model already has knowledge of all these the original data sets. So there are ways in which you can intervene on a trained model and extract this kind of data at inference. We have already looked at adversarial attacks. This also is a kind of intervention, right? You are looking at the FGSM, for instance, fast gradient sign method is a very famous example where, very similar to what we are using for uncertainty estimation, Radfrost, and all the explanations, we backpropagate a loss function gradient to the very first layer, add these noise, add the signs of these noise to the input images, and that's it. You've constructed an adversarial image. So this particular image, which was predicted as a panda with 57% confidence, you add an imperceptible amount of noise, and with 99% confidence, the network now tells you that it's a given, which is completely incorrect, right? So this is another negative intervention. And this particular concept here was also a negative intervention. We already saw this before. As and when you add more prompts, initially itself, the person whoever prompted this, they had the solution, or at least they had close to 55% MIOU. But more they started prompting, it became worse and worse. But the score here, which is the confidence of a neural network, in fact, kept on increasing. So the perception of how good Sam thought it was doing was diverging from what it was actually doing. And this is a negative intervention from the perspective of the user, but they don't know it. They still think that their reasoning for why an exclusion point is here makes sense to the users. So, so we need to ask the question then, should the models be aligned to users, and should the users themselves also align to a model? And if so, what new information should a model give to the user in order to make this kind of inferential alignment? All right, so those are kind of the definitions of positive and negative interventions. I want to very quickly talk about mathematical frameworks that we can use for these kinds of interventions. The one that makes a lot of sense is a causal framework. A causal framework is where interventions are defined. So we want to understand and assess how good a particular intervention is based on a causal framework. I think that is very intuitive. Unfortunately, that works well when you have a causal model available and when the data that you have is something like a tabular data set where data is a little bit more structured data. But when it comes to these kind of images, it's very hard to use these causal principles. Causal inference has about 3 rules, the first of which is insertion and deletion of observations. This requires that factors be inserted and deleted. In this particular case, let's say I am telling you that a causal factor for this image being considered a spoonbill is the beak. So what I need to do is delete this beak and see what the result is going to be. Also, I need to I need to add the beak to something else in order to say if it's a spoonbill or not. So this particular elephant, if I insert this kind of a beak, pass it to the network, if it gives me that the output is a spoonbill, then I should be, I'll assess the fact that the beak is the reason that it is a spoonbill. But obviously, the amount of domain shift that has now been introduced, if I put this beak on top of this elephant and pass it through a neural network, is not something that is easy to accomplish, right? Even with all the generative models that we have right now, this is again not easy to do. This particular rule 1, the same thing with rule 2 as well, where action and observation exchange. So let's say I am now deleting a part of this image. I am deleting the leg of the elephant and so on, replacing with this kind of legs. Again, something that is very hard to do. So all the 3 rules when it comes to causal inference, when we are talking about these kinds of insertion deletion for interventional actions when it comes to images, are very, very hard to accomplish. Not something that's very easy to do, especially even the neural networks themselves, they're not causal models. Even we may start with the assumption that they are, but they are in fact not causal models. So it's hard to say if the output factor that we are assessing is because of the factor that we are assessing, or if it's because of some irregularity within the neural network architecture itself, right? There's also some dangers when it comes to interventions. There is this one explanatory method called RISE, randomized input something explanation. Should have known this. Sorry. One problem with having these kind of names is that RISE is such a nice acronym that you almost forget what it stands for. One of my friends had written a paper called POTUS, by the way, and till this date I have no idea what it was. The first word meant perceptual, but I really don't know what the other ones are. Again, that's an issue when you make these kind of nice acronyms. Randomized input subset explanations, I think. I do believe that is the name. The way it works is that you take an image, you make about 6,000 interventions. So you mask 6,000 different types of masks, pass it through a neural network, you see what the probabilities are, take these probabilities, multiply it with the weights, and convert it into this kind of a explanatory technique. Right? So in other words, what you're doing is you're deleting certain regions and you're weighing the effect of your deletions, which is 0.09 will be multiplied with M1 here, 0.56 will be multiplied with M6000 here, and you're going to get this explanation that you see here on the right-hand side. But there is a danger here because you have only done 6,000 times. And if you do the actual math, there's a very, very large number of actual interventions you can actually do. Right? So you can intervene on the top left pixels, and all will remain as they are. You can intervene on the second pixel, all they are, and then combinations of 2 pixels, combinations of 3 pixels, and so on. So even though there are 6,000 interventions done, they're not really all possible ones. So what we did was we inverted this change. We, instead of saying that we are multiplying with 0.09 with the mask, we multiplied it with the original explanation probability minus the new probability. In other words, in this case, if it was 9.9 probability initially without any masking, RISE explanation does 0.09 multiplied by first mask. What we did was 0.9 minus of 0.09, which is 0.81 multiplied the mask, and use a weighted sum in that way. And we got this kind of explanation. It looks very bad. This is not a good explanation at all. But later down the line, I'll show you in the existing objective explanatory methods, this does much better than this. This is, we have, there's a theory behind why we do the negative here and showing it. It's more like a necessity and sufficiency conditions. Causality has these two conditions. This setup is built for a necessity conditions. If we now remove the necessity and make sufficiency conditions, this is how the result is going to look like. So we use the same intervention setup and constructed this kind of an adversarial example explanation, which looks like this, which is a very bad explanation, but in fact does very well when it comes to the objective metrics. So that is a problem for using these causality metrics. Predictive uncertainty is another way of doing it. And as of now, it seems like a better methodology of constructing a better assessment of these kinds of interventions. But again, this is subject to more research and more thinking about it, essentially, to say one is better than the other. But uncertainty is better than causality when it comes to assessing these kinds of interventions. We are not assessing the interventions themselves, but we are assessing the residual of other interventions that could have happened if not for this particular intervention. And that is how we can say, or we can assure or assess a particular intervention in this case. All right. So I just want to quickly go through a case study in intervention in interpretability. It's basically to show that there's no one-size-fits-all solution when it comes to choosing explanations. Initially, I talked about this way of objectively evaluating explanations, right? We can mask a particular image, pass it through a network, and see if the image remains the same explanation. We are making sure that the expectation of y of Sx2 is greater than y of Sx1 to say that Sx2 is a better explanation when it comes to Sx1. However, the bigger an explanation, the better my objective metric is going to say this particular explanation is. So fine-grained explanations are never going to be chosen when it comes to this type of masking strategies. This is not a good explanation, or this is not a good choice of objective evaluation of explanation when it comes to explainability literature. And this is actually well known within explainability. I think this was used back in 2018, but since then there have been a couple of other papers and objective evaluation metrics that have come out. And at the end of the day, I'll say that, I'll tell you the conclusion, which is that we talk about 3 of these techniques, objective explanations, all of them have their issues. So there is no one size fits all when it comes to intervening on top of these networks in order to say which explanation is better. The second type of way of intervening within explanations is the pixel-wise masking using explanation as importance. So we saw this image. Let's say that this particular pixel here is the reddest of region, that it has the highest importance. So my explanatory technique, whichever it is telling me that that particular pixel is very high importance, while some pixel here has 0, it's completely blue, it's 0, which has the least possible importance. We use the insertion deletion techniques, which is inspired by causality analysis, to start by deleting the highest importance pixel from the network, from the image itself. What we do is step 1, we mask highest important pixel and pass the image through it, and we note down what the probability is. The next step is we take the next highest pixel. Let's say this was 1, this was 0.998. So we take that particular pixel. We have removed 2 pixels right now, and we note down what the probability is. Ideally, the least amount of pixels that we delete, our probability must become as low as possible. That's the way you can measure each explanation against the other. Right? So that is a pixel-wise way of evaluating how good explanations are. In this case, this image is that of a bittern. You see that this is where the explanation needs to be, which is what this explanation is showing you. So you start by deleting this 1 pixel. You see that from 99% or something, it drops a little bit. Then you remove the second pixel, third pixel, and so on. It moves a little bit, your probability decreases a little bit more, and so on. You'll see very quickly that your probability has decreased quite a bit. And now you measure the area under this particular curve, and that area under this curve is going to give you some number. Closer it is to 0, better your explanation is, because it has identified the important pixels within your explanation. Right? And you can do this across different explanations and say which explanation is better than the other. So this is what is called a deletion score. We can also do the opposite, which is an insertion score. You start with full black image, and start by applying one pixel after other. So in this case, you apply the first pixel on a fully black image, you have only one pixel, you see what the output is going to be. Then you put the second pixel in, you see what the output is going to be, and so on. So this is like an insertion method of evaluating explanations. And ideally, very quickly, you want your output to say that this is the correct class. So in this case, for the pattern, you see at around, I would say about 20%, you start having a very high probability for the class of pattern. Ideally, you want this to be 100 or 1, where with one pixel, your network has identified the causal pixel that makes it a pattern, and that is giving you a good approximation, or at least a good prediction. So this is what we call an insertion score. Now, for the, I previously showed you this particular image, right? So this is an adversarial example or an adversarial explanation that is constructed by sufficiency conditions. So there's GradCam, GradCam++, rise, and shape. Shape has the highest and the best objective results when it comes to these kind of objective explanations. The reason is that these kind of pixel-wise insertion deletion, what it does is it gives a higher importance to these pixel-wise results, which is not how human beings we see it. We see structures in data. We don't see pixels. We don't make assessment. We don't have perception based on pixels. We make perception based on structures that exist within image and within scenes. Right? And that's a very important aspect, which is not considered within this kind of insertion, pixel-wise insertion and deletion. And that's why we can construct these bad explanations that will give you a higher amount of insertion and deletion scores when it comes to these objective evaluation metrics. Again, my goal in this entire section is not to say one is better than the other and there is a best thing, rather to show that any choice that you're making as an engineer when you're evaluating your results is going to have something bad associated with it, and that you have to, at the end of the day, assess it based on uncertainty. That is the overarching theme there. But let's look at the third way, which is the structure-wise masking using information. All right, so we just discovered that pixel-wise is bad. Can we do structure-wise? So defining what that structure is very important and very hard. Let's say I'm making that decision and saying that structure-wise is important based on information. More information that exists in a particular structure means that that particular explanation is going to be better. Right? And the way we do it is very similar to the insertion and deletion, except on the x-axis right now, it's the Huffman score of my encoded pixels. So in this particular case, let's say the image of a lung, you have this kind of explanation from GradCam. The red regions, you're looking at what the amount of information encoded within the same corresponding pixels of the red region here, and you're using that information on the x-axis. It's going to be a ratio basically that you're on the x-axis, and y-axis is going to be accuracy. Before, I think it was probability, the insertion deletion. Here it is going to be accuracy. And you use the same kind of setup, except in this case, you're doing insertion deletion, but you're doing insertion deletion of structures, of information in the images rather than pixels. What you see, of course, is that your y-axis is performance and x-axis is going to be a ratio of Huffman encoded masked and original image for explanations that matter. So this is for the deletion, and you can do the same thing for insertion as well. So similar to before, ideally you want 1 for your 0 for your deletion, and you want a very high number for your insertion, right? That part is similar to before, and there are different metrics, different explanatory metrics that you can use to say one is better than the other in this case. But instead of talking about the metrics, I want to showcase the results of these metrics. So this particular method called causal cam is giving you very good in terms of this explanatory evaluation setup. It's giving you a very good insertion score and a very good deletion score. But when you actually look at the explanation, this is how it looks like. You have, this is where this is, I think, COVID and non-COVID data set. So originally the network predicted COVID with 79% accuracy when you showed this part of the image, when you masked this part of the image and gave it in. But when you masked this part of the image and gave it in, it gave you a 91% accuracy. right? So there's a lot of bias that has gone in, and that is the causal thing that has led your network to make this particular decision, or led your explanation or objective evaluation to say this explanation is better than the other, because it has found these kinds of spurious correlations in order to say one method is better than the other method. It's only looking at the amount of information that exists from the perspective of a neural network in this particular case. So whatever you're trying to optimize for, you will be able to, but generally you will not get what you're looking for. Either it won't be similar to how a human being sees it when it comes to pixel-wise insertion deletion, or if you're looking at the information perspective, this can reveal biases, yes, but it's not a good explanation. You cannot show this to doctors and say, this is why it's COVID with probability of 91%. In fact, this is better to say that this is COVID with probability 79%. The true result is, in fact, I hope you can see the red oval here. This is why it, in fact, was diagnosed as COVID in this particular data set. Neither GradCam nor CausalCam, in fact, gave you these kinds of results, but I think the takeaway message is more that any kind of intervenability that you're trying to do is not always going to be positive, and there is going to be some kinds of negative interventions. Most probably there will be these kinds of negative interventions, and the decisions that we are making is many times is going to come down to how bad of a negative intervention that you took, essentially. All right, so that brings us to the last part, which is conclusions and future directions. I think I'm only 5 minutes away, so I'll just quickly go through this. There's not much here. I just wanted to, bring back all the means that we had throughout. It's a very nice way to end up like a 4-hour session. So this is the novel data 1-2 punch. You either don't have novel data to begin with, or even if you do, it's not very easy to say where that novel data needs to be used during training. Should it be in early stages, later stages? It depends on how much data you have. 0-shot inference, 1-shot, few-shot inference, and so on. There's a lot of decisions that you would have to take. Robustness is not easy. There could always be some bad actors who can engineer some results in order to mislead your model. There have to be human beings that are involved in these kinds of situations. There's a lot of work that is done within optimization and data collection to make sure that your model is good during training. But there's not as much work that is done during inference, but there is a lot that we can do, because as we saw earlier, what we use a network for is, we just train it and try to make sure that it's working in its task. But there's a lot of knowledge that is involved within this model construction, and our goal is that we should be able to extract how much of it is possible. Explanation work is uncertainty work. Again, this is more of an opinion, but we truly believe that everything comes down to the fact that a network does not give you a one hot vector as the output. It never tells you something is 100%. It tells you something is 98%, and then you need to ask the question, oh, wait, where did the 2% go? And that analysis is what uncertainty is, that the fact that it's a probability rather than an assertion, what a neural network gives you. And you need to use that to have multiple applications. One of the key takeaways is, of course, gradients. Gradients have a lot of information that you can use. Generally, the way gradients has always been used is from a Fisher information, where it's the Fisher information of likelihood function, but a Fisher information of a loss function also has a lot of information. We use this during training, but we should also use it during inference and testing, and utilize that information either from model retraining, your second stage of inference, which is in introspective learning, or quantification of uncertainty, explainability, or any other kind of applications that we choose to do so. There's a lot of future directions in this kind of research. The first, most important, being this kind of test time augmentation research. Test time augmentation generally means that we take our data point, make some changes on it, pass it through the network, and then see what the results are and try to find some kind of a variance through it. But it's not always good. Ideally, what we want is the network telling us what it needs from us, and that's where the active inference part comes in. We do want to make sure that as much uncertainty is quantified, and we utilize this kind of uncertainty and use it as much as possible as well. And these kind of test time interventions for AI alignment. We always think that something like RLHF and DPO, direct preference optimization, we want to align a model to a user, but there is also a case to be made that the user is also aligned towards how a model functions as well. A user, in fact, is better adapted. It's easier for a user to adapt towards how a model functions than the opposite case. So, there has to be test time alignment. We only went through a few of references, but there's a lot more that we have worked on. But over the last 3.5 hours, we only went through about 3 or 4 case studies, but all the listed applications that we have works on top of it, and these 15 basically give you that. All right, with that, I think we will end this session. We have 1 more minute, but we'll be around here. So if you have any questions, you're more than welcome to ask us and talk to us. Thank you. Oh.
So for those who came late, I can download the materials from this QR code. Thank you.
Yep.
Thank you for the great talk.
Of course, yeah.
Yeah. So I just saw what's the one.
And with whole stack method is also kind of the same, that you wait for the model to make a decision.